in particular to DBMS course? Anything that you guys want to share?
Excuse me, sir. I want to share something
Go
about
ahead.
DBMS only. So I'm first time learning the DBMS thing. Okay. So it is not very hard to understand the subject, but it is really vast. You
Correct.
have to go through each and every point and
Correct.
memorize or remember each and everything. So I think that's a very vast syllabus in quiz one. So I
Yeah.
faced that. Yeah.
Yeah, exactly. In quiz 2, you will see this more, more difficulty will come. So
Is it
the,
more in quiz two?
yeah, it's more. Obviously, it's more. In quiz 1, it is still okay, but in quiz 2, again, you have to solve a lot of questions. Then, okay, so yeah, this is something that we already hear every year, and very sadly, we have also devised. I mean, we have also told the planning committee about this, and every time we get the same answer that since in IIT the semester system is based in trimester or semester is based in this manner, and if you want to do it in a trimester basis, then you have to, I mean, and you also want to put all the things that you need to teach in a subject all together, and you want to have a trimester based system, then this is how it has to be. And yeah, so we also can't put a lot of pressure on planning committee, because we as regular student of IITM, we also go through the same ragda or the same hustle in our courses, that you have to learn a lot of stuff together. So yeah, this is a complaint that not only you guys have, but we also have from our let's say our professors.
But sir, a
Anyway,
subject is really interesting. It's
uh,
interesting to study. Yeah. And
correct,
enjoyable. Yeah, it is
correct.
not get bored at any time, but it is really vast.
I
Yes,
mean, sir,
yeah,
I
it
will
is.
suggest like a subject, a concept wise is good. I will say. I think we need more question banks and like things we can practice. Like, I mean, you practice a lot of PYQs and you go to like quiz and you see new questions popping up. Especially, I saw that happening in Mad One. I mean,
Correct.
if we are trained enough with multiple types of questions, I think it is an enjoyable subject. We can enjoy it.
The thing is, multiple question is fine, and yeah, that is you're correct, completely correct. But then again, if solving every question takes time, so even if you even we can give you a plethora of question by tomorrow. The problem is, will you be able to solve it, all of them? I mean, I'm not talking about whether you will be able to. What I mean is whether you will be able to manage time. I mean, that's the same problem again, right? If the content is more, you don't even have a lot of time to digest the fundamental theory or the main part. Practicing again comes later. So anyway, if the syllabus is vast, it is difficult, and we hear it every time, and we are sorry for that. Nothing can be done. But what I want to address more
The
importantly,
things is happening is like we are getting graded assignments only 10 marks. Consideration to that, it's the difficulty level is too much, because in colleges and all there is like not amounting to 10 marks is considered for internals. So we have only ourselves 90% gradings. So that should be like should increase some marks to the graded assignments as well.
My
okay, can you
that
restate it? I couldn't quite catch it. What you want, the point?
Like the point is we are just getting 90% of the scorings by ourselves, and we have to just things are not like internal marks are only 10 out of 100. So we are considered about going to like we have to just things are not we are only 90% are scored by quizzes.
Mayur, I think discussing that thing won't make any sense because that is not up to you and me, or even I think PODs, if they can discuss it, fine with that. But that is something upon IITM to decide the grading system. What we can discuss over here is like if we have multiple set of questions, that if we are equipped enough like with questions, yeah, if we shoot any sort of question with us, we'll fight with it. But that only I will request you, sir, because right now we are entering in the domain where like mathematics is like slowly like coming in. Week 5 we saw, week 6 more will be there integration. So if you have multiple questions to give us, I mean I can manage. You
Okay,
provide us
fine.
questions, I will
Okay,
solve it, and so that I'm well equipped with for the this quiz too.
okay, fine. So then I think I got Mayur's point also. See, yeah, so I think I will agree with Shivam on that point, Mayur. There are, I mean, we can convey your message, but again, this is the same thing. Even about the structure, it was decided in this manner only. So somehow that is not in our hand, and that is not in anyone's hand actually. This is how the system works. In normal colleges, I mean, it's a bit difficult to compare like that because here the weightage is on some different aspects, and that's how we judge. I understand your point, but then again, it's nothing that we can do a lot about. But by suggestion of giving questions, I think first of all, you guys can miss one thing. So in the slides, for particularly week 5 and week 6 in the normalization, lossless decomposition, those kind of questions, there are many example questions given to you, but the problem is, again, I don't think that the solution is given. I mean, only the questions are given. So yeah, that is something we will take note of. Maybe we will give some solutions, only the end solution, so that you guys can solve it and maybe have a better understanding of those questions, because some questions, quite a lot of questions are already given in the slide. So anyway, so okay, one important point that I was trying to discuss here, that is, see, from a practical standpoint, whatever we will learn in week 5, week 6, week 7, all of these things, DBMS is a systems oriented course, like operating system, like we don't do compiler as of now, but compiler is coming very soon. Compiler design, database management system. So these fall into a systems domain of computer science. Okay, now the thing is, when you guys will, let's say many of you are trying, I mean, are doing these courses for the primary aim of moving into industry or something like that, and some of you are maybe doing it as a hobby or something, but most of you are trying as a career option. The point is, when you move into industry, right, unless and until you are going for a very selective and specific role of database architect or data engineer, not all data engineer does this kind of thing, but data engineer with a very specific responsibility of designing or maybe making or planning the database schema, data, these things. So those people will work with these normalization stuff and how to plan these things, how to advise the schema of a database, all these things. Okay, and that also if you are working on relational database. So most of you would not work with so much detail like we will learn in week 5, week 6, I mean in the subsequent weeks also. But very important point is, unless and until you have a basic overview of the all the week's content, you can't work properly even in the domain that you will work. Okay, I mean, because most of you, if you go into the data science domain also, even if you have to work with, let's say, writing SQL query, so practically speaking, if you are going into some analysis kind of job, data analyst or data scientist or whatever, 90% of the time you will deal with SQL only. Okay, you don't have to worry about all these internal matters of database management systems. Most of the time it will be SQL. And yeah, as I told, some people who are going into the database architect kind of profile, if some of you go, they will be working on this database schema design and all of that. But most of you will work on SQL queries. The point is, if you, while writing SQL queries, now the days have come in such a manner that you all you need to do is write a prompt, right? Maybe this was not earlier, but now industries are basically writing, I mean, saying engineers to write prompt. If you can't write some complicated query, your LLMs will give it. Unless, I mean, there are some token restrictions and all of that in industry. I mean, you cannot use LLM as much as you want because it takes some money. So there are some tokens given, and you can use those tokens with some limited conditions are there, and then they write the SQL query. What's more important to observe over here is, okay, LLMs and all these things can give you query. I mean, your chat GPT and whatever, they can give you the query. But the problem is they are not very good at optimizing, and they are not very good at choosing. I mean, the internal models are there which can do specific tasks like optimization, but generally speaking, they are not good at that. So if you are working as a data analyst or as a data scientist who is fetching data or doing data pre-processing or stuffs like that in your industry domain when you are working, then you have to be very nowadays, earlier it might not be required, but nowadays you have to be very familiar with how the internals work. Because if you are aware of that, then only you can say that, okay, this SQL query and SQL query number 1, SQL query number 2, both fetches the same result set. Only thing is, I mean, this is obviously there, right? You guys have done SQL, so you guys must be aware of this fact that you can write multiple queries to fetch the same result set. So two or more SQL queries can fetch the same result set, but their performance will be different. Now we have not gone into that aspect of SQL, and we will do that actually in week 11, I think. Yeah, week 11 or week 10 or 11. So we will do that. That which query is performing better, which query is performing bad. I mean, not worse. It fetches the same result set, but one query might work better, another query might not work better. So this is where your part comes, right? This is where your LLMs and all this AI or whatever you want to call them, they are not that much good at. Okay, so not that much good. I mean, yeah. So obviously there are also some modularities in this, but mostly speaking, they are not that much good. So you need to understand the internals of systems if you really want to shine in career nowadays, because normal SQL query writing, I mean, I'm talking in perspective of DBMS course, because writing SQL query, I think for those who are going into industry is the most important thing that you must take out of this course. Okay, even if you do not know anything else and just know SQL, that also will work for you in industry. I mean, as long as you are going for analyst kind of role. But that also is not working now, because the industry is changing hugely, and you guys are aware of this, I hope. So now what you must be aware of is the system internals, because once you are aware of that, those things, then you can figure out these kind of modularities, that okay, this query, both are same. Both queries can be written by the LLM, but I know as a guy who knows DBMS properly, that which one is better and which one is worse on the basis of performance optimization, some other features. The point is, in order to judge that, in order to realize that which query is better, you must know the internals of how the database works. I mean, so you understand, right? So I mean, we will cover all those topics now. Week 7, week 8, all these things will come. So therefore, why I am saying this before starting this session is because many of you will not be able to relate to what we will discuss in week 5, week 6, and all the subsequent weeks. Right? Many of you might have the feeling that okay, yaar, ye matlab, I mean, okay, I am doing some complicated theoretical stuff, and it is not at all beneficial for me, because when I am basically creating a website and adding a DBMS at backend, then I'm not doing anything very related to what I'm learning in these weeks. So this feeling will come. Problem is, yeah, that is there, but because when you are basically adding a database in backend, you are not aware of all the things that is happening internally. You are not required to be aware of all of that. But when you really go to some job and you are writing real enterprise level software, and that time you have to fetch something, some data set, something, or do some work, then performance and scalability are two very important points that we do not realize when we are doing our hobby projects, when we are kind of improving our GitHub repository and all of that. Performance and scalability. Okay, a same query, a same web page can be created in 10 different types of ways. The thing is, when you want to scale it, what will be the nuances of that? And the second is, how is it performing? In how much lesser amount of hardware can I gain that much amount of performance on the software side? So these two features are very important, and in order to understand these two features, in order to write a responsive, efficient, optimized code or optimized query or whatever, right? I mean, optimized upper level software, you need to understand system internals. Then only you can do that. Now, initially, it was not required for maybe 5 years, not even 5 years, even 3 years later, 3 years earlier, it was not required that much. I mean, yeah. So people in interview would only ask you SQL query. Yeah, tell me how can you write this query? Now, in good companies will not ask you just how to write a query. They will ask you why this query is doing good and why this query is not doing good. So be aware of this fact and don't get disheartened if you cannot relate with what you are learning in week 5, week 6. But please be aware that these things will be very essential in the coming days. Okay, I mean, I can speak this very confidently because maybe 3 years earlier it wouldn't have been required, but now it is very much required. Okay, so yeah, bear with it. If you do not understand something, go through the hustle. I think it will be beneficial for you later. Okay, now enough talking. Let's start. Anyone wants to say something? Go ahead before I start today's session. Chalo. Fine. So week 5, how many of you have, I mean, you guys are comfortable with, I mean, raise your hand and be honest about it. Okay. Week 5 content, not week 6. We will discuss week 6 in this session. What I'm talking about is week 5 content. How many of you are uh, understood the things? 6, 7, 7, 8. Others are not quite confident. They are. So the problem is, if that is the situation, then discussing week 6 is very difficult. Okay, anyways, let us try to somehow. So I would say it like this. What did we learn in week 5? If you have a brief discussion, not in detail, I mean, just I will tell that thing. See, in week 5, we learned about, okay, what are database keys, how to find candidate keys and stuff like that. Okay, and then we learned about functional dependencies. What are functional dependencies? Why a functional dependency is important, and I think one very, very important point that is not generally discussed, and that is why many students get confused about is what we start. I mean, any DBMS course you see, what generally people do is, okay, you have functional dependency. When the left, I mean, A attribute functionality determines B attribute. That means whenever A attribute is repeating, B attribute must repeat. It should not be different. So that is kind of the definition of functional dependency, and then you move into solving examples. But from your real understanding point of view, let me re-ask that question. How are functional dependency really generated in when you are working with real life projects? Can someone answer that? I want to discuss that thing once again. How do you get these functional dependencies? From where does it come? Does it come from the table of data that you create? I mean, the data set, maybe a lot of data is given to you in an Excel file, and from that you need to somehow make a database schema or tables and all of that, and you want to convert that Excel file system into a database system or something like that, right? You have been given a data and you want to create a database out of it as a database architect or as a schema designer. So from where does this functional dependency comes? Anyone wants to say? Go ahead. अरे यार क्या हो गया? Am I not audible?
Audible, sir.
Okay, no one wants to say something. Any idea? Give me wrong answer also. So what is your idea? How did you get functional dependency? I hope you guys know functional dependencies.
Sir, is it given to us, sir?
How is it given to us? Any guess? I mean, I'm not asking question, I'm discussing. Yeah.
By the people who are
Does it
engaging
comes
us?
from the attributes of the set of attributes of a table linked with the database?
Okay, so you make a table, you have a set of attributes. Attribute means basically columns. So the columns of the table, okay, no, fine. Then, so from the columns of the table, you will get the functional dependency. So what are functional dependency? As I said that let us, if we have a table and we have multiple, let's say these columns, AB, I mean not AB, let's say roll number, okay, let's say name, let's say class of a student, marks, whatever, dot, 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 different fields. So we say that if we use these field names completely while solving our questions, then it's kind of cumbersome. You have to write the whole field name, like roll number determines, let's say, name, right? Something like this. So all the time. So because this is writing, these field names are difficult, so we use these aliases ABCD. A for roll number, B for name. So that is how we get these aliases. That is one simple thing. Secondly, how do we get this? So roll number determines name. So we have this table, we have this attributes. As I think one of you were saying that it has been, maybe it is given to us. So yeah, that is actually correct. It is given to us. Now the thing is, see, first of all, our idea while learning many DBMS courses is that a table is given to us, the data is filled up in the table, and if we see that if roll number, so like this alpha and beta, you might have seen many such example, alpha beta. If alpha is, let's say, A1, beta is B1, A2, let's say B2, let's say then A3, then again B1, then A2, then let's say B4. Like, let's say suppose something like this is given, then you apply the condition of functional dependency. Okay, if alpha goes to beta will be a functional dependency only when the values of alpha are repeating, then the beta's values are also repeating, I mean the same value is there. So A1 B1, okay, A3 B1, that is also fine. See, I said if alpha is repeating, then only beta has to repeat. Beta can repeat for different alpha also, that is not a problem. But if alpha is repeating, then necessarily beta has to repeat. That is the definition of functional dependency. So A3 B1 will not violate any functional dependency criteria with respect to A1 B1. That B1 is there with A1, how can B1 be again be there with A3? That is not a problem. It can be there. So alpha goes to beta can still be a functional dependency. But then again, this cannot happen because A2 B2 was already there, but when A2 is getting repeated, B4 is coming here. So then this is not a functional dependency. So what I mean to say is that we kind of derive in most DBMS courses, we have this idea that a table is there, data is there, from there we derive the functional dependency. No, this is how we study in order to understand the definition of functional dependency. In real life, nothing like that happens. Functional dependencies are business rules, are business constraints that are given to you by the client side. Okay, those guys will, whenever the people talk, right, some bank or some company or some whatever XYZ, the client, whoever is giving your company project to make this database system, so they will give you some business rules that these are the things that I want according to their business operations. So those rules are converted into functional dependency, not converted also, those rules are direct, let's say, representation of the functional dependency, because functional dependency are constraints. Like, for example, if a bank is giving you project, so then maybe the functional dependency is a constraint or a business rule is the customer ID should be unique. So the every customer ID must be mapped with a let's say some this is the name and this is this accounts, savings accounts and current accounts and whatever accounts are there. Then all of that should be uniquely one-to-one mapped with a particular customer ID. So the customer ID is the primary key kind of field. So this is one important business rule with respect to bank. So that is your unique identifier, customer ID. Correct. But then that is itself a functional dependency. Then I will write that customer ID functionally determines, let's say, whatever, some savings account, other fields. Right. So something like this. So that means this savings account cannot occur for another customer ID. Okay. Now don't say that account can be having a joint ownership. I'm not
Sir,
going. Yeah. Yeah.
Sir, in short, what is functional dependency?
Okay, that I will not discuss. That I did just now, but then again, this is previous week's content, so I will not do that. Sorry for that. You should be aware of it.
Only one word.
Okay, so I told you now that if I will write alpha functionally this arrow means function dependency. So alpha goes to beta, alpha function determines beta means your the values in alpha column, whenever they are repeating, the values in beta column must be repeating, must repeat. So if A1 B1 is there, so if again A1 is occurring again, repeated again in the over here in the left column, then it should be mapped with B1 again. So here, let's say if I write A1 again, then here B1 should be there compulsorily. It cannot be B3 or B4 or anything else. It should be B1 compulsory. If that is the case for every value, then I can say alpha determines beta. Okay.
Yes, sir.
Okay. So therefore, this is the way we get functional dependencies. Fine. That is point one. From business rules, and then on the basis of these functional dependencies, by keeping these functional dependencies in mind and some rules and some aspects, some constraints in mind, we create we design the database table. So this is our step 2. So first step is gaining the business rules from the client side. So after I get getting the business rule. Now once I get the business rules, on the basis of that I will have some constraints. On the basis of those constraints I will create the table. Not from the table I will derive functional dependency. Okay, that might get derived later also, but that is not permanent. So let me ask you this question. You have a, think it in terms of real life situation. You have a bank database. Now you have a table. Table has some pre-populated value, like ye banda hai abhi bank ke account mein. You have these people in the banks, right? You have a data and a data set of people and their details and everything is there. Now, assuming that we derive functional dependency from table, and let's say you have some proper trend going on in the table data, and from that you basically derive that, okay, this attribute or this column is functionally determining some different column or different attribute. So you derive that. Okay, now next thing that happens is a new customer comes, and the data that the data corresponding to his entry, that is not following the previous functional dependency. The one that you derived based on the earlier data present in the table. It might happen. Okay, so then what do you do? Got the point. So that is why it is not that we derive functional dependency on the basis of table. That we do in our courses, in many courses, any course you see, DBMS, this is how we do for the study purpose. But in real life, that's not the way it really works. Right? In order to understand the definition of functional dependency, we derive it like this from table data, because once you see the table data, you can understand what is happening. Even I just gave the example of functional dependency by saying if A1 is repeated, then B1 must repeat. So that is for understanding purpose. But please understand this, because this is a very fundamental doubt, and later we got this feedback from many industry people that they don't even know what is the sequence of creating a database, and they have done database course with very good marks. How is it possible? So yeah, please have this basic understanding. You don't derive functional dependency from the data set. Functional dependencies are constraint on the basis of which you create the table. Okay, and you make the table. According to that, the tables are created. Fine. And the data that are populated in the table are created following those functional dependencies. Now, till this point, is it clear? Any doubt in this point? Till this point.
No, sir.
Okay, fine. So now once this is done, now once you have created the table, now comes another part, that is optimization and consistency. These 2 points. So first I will say consistency. Now this is again, I think, week 5 content. Consistency. Optimization, let us not discuss as of now. We will do that later. Consistency. So what do you mean by consistency? So if you have repeated values in the table, so this again, I will say it is week 5 contents. I will not go in detail, but briefly I will mention. So if you have, let's say, same the student ID, student name, and some other field, whatever subject, some subject that the student has taken, something like this. Okay, and let's say not subject. Let us make it address. So you have the student address. Okay, now what happens is you have the student ID over here, some is 003, and some name is, let's say, I don't even, Raj. Okay, so fine. So Raj is one name, and then he has some address at Kolkata, let us suppose. Okay, and then what happens is that Raj has changed his location, and okay, another point is, let's say there are many such entries, and somehow later also at some point you have another entry repeated again. Raj is only there, S003 Raj, and let us say there is another field subject. Let us take that subject field as of now. And here, let's say the first subject that we had corresponding to Raj is maths. And then again, we have another subject over here is physics. Okay, and now the thing is, the time when Raj took the physics course, his address was changed to Mumbai. So let's say he moved to Mumbai, and then only he took the physics course. If you want to relate it, let's say this is the database of a online education system, education like BS degree database itself. Consider that. Now you were initially at Kolkata, and then you did the math course in your your foundation, and let's say then there is one physics course in your diploma level. But when you are doing the diploma courses, you have moved to Mumbai due to some reason. So now the next entry that came into this table is Mumbai after some point. So there are many such entries in between. Okay, some Raj, Rohan, Sita, Geeta, whatever. Many such entries are there. So the student database table has this kind of entry. Now what happens? See, the problem is now there are 2 addresses corresponding to the same person, Raj. Okay, this is one troublesome situation. Why? Because later, let's say, address cannot be like city, right? So let's say there is something like Mumbai Mud Island. Okay. My goodness, Mud Island, pehle hi Mud Island mein. But anyways, and there is Lake Town, Kolkata. Okay, so suppose this was his address, but later after moving to Mumbai also, he might want to shift his location to some other place. So now maybe he has moved to some Borivali in Mumbai. Okay, new entry is entered. Now the thing is, and when he's taking this thing, then maybe he's doing the chemistry course. Same Raj, S003. Now see, the problem with having this kind of database is, if you are updating at one place, then the update is not reflected, might not get reflected in all the corresponding entries which you have with respect to Raj. Now let's say the professor who has taught physics wants to contact Raj somehow. Okay, so then he will say that, okay, he is not aware of the other courses Raj has done. So he knows that this student has done my course. So then he wants to contact Raj. How will we contact? He will just go to the database of his course, and he will see that, okay, since my course, I mean, his course is physics. So that's why that database will only show that Raj, and he is staying in Mud Island in Mumbai. Maybe that person sent a letter to Raj at Mud Island address. And that address is no more valid because now Raj is staying at Borivali. So the latest update is not reflected over here. So these are the problems that you might have if you have multiple entries corresponding to a same person or same entity in your table. So this is what we call redundancy. So because you have redundant entries for the same, let's say, entity set, or not entity set, what I mean is same object or same element, you have redundancy. And because of this redundancy, you are having inconsistency. Why? Because this is inconsistent, different addresses for the same person. That is also true in their own aspect, but then again, this is not true when you look at it from the final point, right? At the last time, if you look at it, then it is not correct. So therefore, we are having this inconsistency because of having this redundancy. So somehow, if I can eliminate this redundancy, if I can eliminate the multiple existence of same entry, then we can actually say that, okay, then we will not have this problem. If I can enforce that whatever update will happen with respect to Raj must be happening at one particular place. There should be only one entry, and that should be updated with the latest value. Then every time some changes happen, then that these kind of issues will not occur. I mean, those changes will be reflected. The latest entry will be there. Any person who wants to refer to Raj's current address or Raj's current, fields, database fields, right? So therefore, whenever there is redundancy in the table, we get into inconsistency. Now, or you can also tell these anomalies. Now, the technical term is anomalies. Anomalies means this some problem. Anomaly means some problem, right? And the term anomaly means some problem. So there are three kinds of problem, which are basically update anomaly, insert anomaly, delete anomaly. As you can kind of guess it, that here it is update anomaly because you have updated the address and then the latest address is not reflected at every entry, and that's why you are having this inconsistent behavior. So this is update anomaly. There can also be insert anomaly. So let's say you are not aware that the data is already there and you are reinserting it with some other values. So it is already there. You should have made an update over there, but you are not aware and you are inserting a new value. And then that will lead to update anomaly in return. I mean, sorry, in turn. Okay, later on. So there, I will, yeah.
In short, what are we are targeting? What is that aspect of your so much of description?
I want to reduce redundancy, as I said, because why? The problem with having this much same, as I told now, that if the physics professor wants to contact Raj, when Raj has already moved to Borivali, then the address is not reflected. The latest address is not reflected. Now, why the latest address is not reflected? Because that guy will only see this entry. Because he has not access to chemistry course, and therefore he will not see the updated value inside the chemistry's file. He will only have the entries corresponding to Raj. He has done physics, and when he has done physics, this was his address. After that, Raj has changed address, but this value will not be there with the physics professor. So if he wants to contact Raj, then he will send a letter to this address, and that will not reach Raj because now Raj has changed address. Now, why is this occurring? Because there are multiple entries with respect to Raj. Okay, if I would have only one entry with the current address, then these things would not have occurred.
So how we are able to reduce this redundancy?
That we are coming. That is already there in week 5 again, but that is where we are coming. So this is the trouble. Down there are three kinds of other issues also, and you guys should refer to that. That is update anomaly, insert anomaly, and delete anomaly. All these three anomalies will happen, or inconsistencies will happen when you have redundancy, when you have multiple entries in the table with respect to the same element. So therefore, now coming to your answer, the solution to this is reduce redundancy, or eliminate, not reduce, eliminate redundancy. That is basically eliminate multiple storage of information for the same person or same entity. So yeah, now how can we do that? The process to do that is, fine. So the way to do that is we will follow a set of procedure with some rules, and I mean those rules, if you look at it into depth, you will understand they are nothing but just beautiful observations by seeing the data set, right? You derive some rules by observing the data set, and those rules, but every time we cannot observe the database and figure out what we have to do. So therefore we, by observing the data set, some intelligent and smart people have devised some rules, and you can directly apply those rules on any database to eliminate redundancy. And those set of rules, or stages, we do it in stages, okay? And those set of rules in each stage will give you a better database with respect to lesser redundancy. So let's say we will discuss that. So you have different normal forms, we call them normal forms. Normal forms. Okay, so we have 1NF, or first normal form, like the 2NF, 3NF. Likewise, we will have BCNF. BC is the two person on whose name we create this normal form. It is boys and cod normal form. And then again we have some other aspects of normal form, as like 4NF, 5NF, even 6NF is also there, but those are quite less referred, I mean less popular. We don't generally go to those forms of database, because I mean whatever redundancy you have generally gets eliminated till BCNF. Okay, and going further, so we have 2NF, by the way. Okay, 2NF, 3NF, and then we have BCNF. So we will discuss all these forms till BCNF. 4NF also will discuss, but the thing is, you might just know that we have other forms as well, 4NF, 5NF, better forms as well, but generally we do not go to this form. It is not generally required, because you get enough level of redundancy elimination till BCNF, right? Till 3NF only you get. BCNF is also kind of a overkill sometimes, but still sometimes you may need to go till BCNF, but 4NF, 5NF generally less times we go. But we will learn 4NF, just a little bit we will learn, but anyways. So the thing is, to eliminate redundancy, we will follow some stages, and each stage will have some rules. And stages means we will apply some things, some task we will do on the database, on each table of the database, and then we will convert that table into one of the normal forms. So let's say there is one table, a normal table, and we will have some rules. Each and we will see that whether those rules are being followed in the table or not. If the table follows those rules, we will say that okay, then this particular table is in that particular normal form corresponding to the rules. So as I said, each normal form will have some rules. We will see that whether the rules of that normal form is followed in that table or not. If that table follows those rules of that normal form, then we will say that okay, this table is in this particular normal form. Okay, and then we will try to improve it further to, or take it further to the next normal form if possible, and if we want it, right? So then we will take it to the next normal form by applying some rules. So how will we do it? So first thing is, we have understand the structure, because the rules and everything is fine, that is on the basis of practice. You guys will practice and you will learn, but understand this, what we are going to do and why we are going to do it. We have some checking rules for each normal form. Apply these checking rules on each table and see whether the table is in a particular normal form or not. Okay, then you see if table is in that normal form, then then it's your choice. You want to keep it at that level only, fine, then your choice. And if you want to improve it further, so keep it at that, I mean, keep it as it is. That is your first choice. Second choice is improve further. Improve further means reduce further redundancy. So in order to do that, you have to go one more level of normalization, that is to the next normal form, which is your next normal form. But how can we reach this next normal form? Like in initial first step, we had this checking rules to check whether the table is in the particular normal form or not. Now, in order to convert that table into the next normal form, again, we have some application rules. Not rules, application, yeah, you can say rules. Application, I will say application task. Some things you have to do. On the basis of some rules, obviously. On the basis of some predetermined rules. Fine. On the basis of this, you convert the table into a better normal form table, and that means improving. Improving means reducing redundancy. Further redundancy. Every time you go one step ahead, you get lesser redundancy in the table. Fine. So likewise, we will reach one of the normal form, and then we will see that, okay, we have done enough reduction in redundancy. There are no repetitions of data. So now we have a database which is very hard to get into an inconsistent state. Even if we insert new data, update data, delete data, whatever the three kinds of anomalies that were occurring, insert anomaly, delete anomaly, and update anomaly, no anomaly will occur now, because now our data has very less or no redundancy, and therefore we are fine with it. So now that is what we call database designing, that you are optimizing the database in such a manner so that you do not get into inconsistent state. There is no, wrong data present in the database or multiple copies of the data present in the database. Now you guys, those who have not seen the lecture properly, you guys might have one feeling that, yaar, why is it so much difficult? I mean, there is some repetition of data. Okay, just keep it one Raj. I mean, let's take this example. Okay, Raj was there and we have these 3 entries. Let's take Raj and keep one entry, and whenever the update happens, we will just do it in one place. Itna hi to hai, bas we have to do this much. Then what is the trouble? See, the trouble is that as we go in these normal forms now, we will move now. You will see that redundancy might not always be very much as observable as we just saw in the example. Redundancy might be transitive. That is, we will see that, but it is not always easy to observe. Okay, it might be there in the table and you may not realize it. So therefore, it is important to follow these rules so that these redundancies get eliminated. If you pay close attention, you will see the redundancy is there. But most probably you will not see it with your open eyes every time. That's why it is important to follow the rules and check that if the table is in the particular normal form or not. Right. Okay, now I will move to one normal form and see the rules and everything, and we will see the process of normalization. Yeah, before that, is the context clear, or anyone has any doubt, ask. Okay, no doubt.
Sir, in the last slide, I want to ask one thing.
Just a second. By the way, just one more thing, as I said earlier also, if any one of you has any doubt, please interrupt me in between. Don't wait for the last, because I will not be able to see your raised hand and things. Yeah.
So this changing rules as like application to improve that. But how like checking rules are every like 1NF, 2NF, 3NF. These rules are, we have to like learn them.
Yeah, obviously. I mean, yeah, it will take just 1 or 2. This is not like we have given you 10 rules, you have to apply 10 rules. It's not, we will go through the process. Just see that it's not that much difficult. Okay. So that's why week 5 is important, because now once we go into the normalization, if you are comfortable with week 5, then you will see that this is very easy. I mean, very, very easy, nothing difficult. But if you are not comfortable with topics like finding candidate keys, finding functional dependencies, covering of functional dependencies, minimal cover, all those, not minimal cover, even covering of functional dependency, is it clear? Then it will be fine. So those topics should be
already in fourth week also, no?
Week 4, I don't think it is there in that much detail, but week 5 was mainly about this. right? Functional
We
dependencies.
are currently talking about week 6 or week 5.
Week 6, week 6.
Okay.
Week 7 is already released. We are talking about week 6.
Okay.
So week 5 contents you should be comfortable with. That's why I asked. Anyways, maybe we will do some while discussing. We will do anyway. I discussed what are functional dependency, what are all these things. I will discuss briefly as much as possible, but still be comfortable with week 5. Otherwise, you will not understand normalization. Fine. So let's start with the first normal form. Right. So what is first normal form? First normal form is basically any table where you do not have multi-valued dependency. Not multi-valued dependency, sorry, multi-valued attributes. Sorry, not multi-valued dependency. Okay, I mean multi-valued attributes. So where the table is, if I briefly in a crude language, if I say where the table is flat and atomic. Now, what do we mean by these things? In your ER diagram section, we discussed that there can be two different things. First is composite attribute, and the second is multi-valued attribute. Can anyone tell me what is composite attribute? You guys have given quiz 1. So, what is composite attribute?
Composites are which are 2.
So where more than 2-3 fields are composed together and we give a same name, like let's say first name, middle name. Very common example of a composite attribute is first name, middle name, last name. We club these 3 different attributes together and say that this is one attribute. So in that, basically these are 3 different string fields. While you write the create table query, you have these 3 separate string fields or varchar fields. I mean varchar fields, but then you can compose them together and say that this is one composite name attribute. I mean, you can have an alias called name and then say this is a name which consists of 3 varchar fields. But that is what we call a composite attribute, and we should not have that in a ER diagram representation. If we, I mean, not should not. If it is there, then we do some task anyways. And then another thing is there, we have the multi-valued attribute. Now, multi-valued attributes are what? Corresponding to a given entry, you have different values in that attribute. So if I have 2 or 3 phone numbers, then corresponding to my name, I have in the phone number column, I have 3 phone numbers given. I mean, I have given 3 phone numbers and it is stored in the same row. We have 3 phone numbers, right? So let's say in the name field, I have my name, and then in the phone number field, I have some, let's say P1, P2, P3, 3 phone numbers I have given. Now, this is what we call a multi-valued attribute. Now, if this is there in a table, then we need to do what in ER diagram perspective?
We have to create another table.
Correct. So we have to create another table in which we have again this name field and phone field only and nothing else. Let's say here I had address and other fields as well, right? But here only we will have name and phone. This is our table 2. These are table 1. So this we will have name and phone, and here I will have my name, right? And then we have P1, P2, P3 divided into 3 separate rows. Okay. Fine. So this is what we had to do in ER diagram idea. So once we convert it into this form, then again this is a proper table, right? And if there are multi-valued attributes, then we will break it down like in T2 in this format. So if we have done that,
once more tell what is happening.
Yeah, so simple. If you have multiple attribute values, sorry, I said 3 phone numbers I have given. Now these 3 phone numbers are there inside one row only. So suppose these are the rows, right? Bhaskar, and then let's say some Raj is there, right? Let's say Geeta is there, right? Different rows are there. So if I have multiple rows and then let's say Geeta has given only one phone number, right? So let's say G1 is Geeta's phone number, R1 is Raj's phone number, but I have given 3 phone number. If a table has these kind of entries where you have multiple value in attribute, then you break that down into this kind of way. You have a name, I mean in this new table format, T2 table, you break it down, and where you have only the name and phone attribute. You will not have any other attribute in this table. As I said that let's say in the original table you have address, you have some, let's say some other serial number, roll number, marks, some other fields are also there, right? But in the new table, you will not have any other attribute. You will have only the primary key, assuming that name is the primary key over here. You will only have the primary key attribute, and you will have the corresponding that multi-valued attribute field. And then you will break it down into different rows. Now here it is different rows. So basically we are keeping the row atomic. You cannot have multiple values in a same row. That is the rule.
If Sir Bhaskar has 3 phone numbers, then the table 2 will have corresponding 3 numbers and rows will be split into it.
Yeah, that's what I said. Now you have 3 different phone numbers, and therefore you are splitting it into 3 different rows. Okay, fine. So if you have done this task, then it is already in one first normal form, right? Your table where you do not have any multi-valued attributes and it is a flat atomic table, then you call it as a already it is 1NF. You do not have to check. So that is the rule. I told you you have 2 things to follow: checking rules in order to define whether a particular table is in a particular normal form or not. Second rule is when you want to convert the table into a 1 level up normal form, maybe 2NF, maybe 3NF, whatever, then you have to apply some changes on the basis of some rules. Now those are application rules. Now we will see the application rules now. But the first check for the first normal form, the checking rule is that whether the given table is in a norm is in 1NF or not. Only thing is you have to check whether there are multi-valued attribute. If it is there, you say that okay, then it is not in 1NF. If the table is a flat table, that is there are no multi-valued attribute, then you can say then yeah, now the table is a 1NF table. Got the point? So now that is 1NF. Simple. Over. 1NF is very simple. Now we will go to second normal form. Now I want someone to tell me what are candidate keys. I wouldn't have asked this, but kind of most of you have not done week 5, so that's why I am asking this. What are candidate keys?
Values.
Sorry, repeat again.
Unique values.
Unique values. Anyone else?
It is a
Keys.
minimal of hello sir.
Minimal.
Minimal of
unique-
super.
Minimal of super key. I think one girl was saying something. Go ahead.
Yes, sir. Those are those attributes whose closure will give us all the other attributes.
Nice answer. Yeah, correct. So that is attribute whose closure will give me all the other attributes. Simple answer. But yeah, so this is the thing. What basically means is unique value is kind of correct, but when you say unique value, I mean, what's unique value are you telling? That particular attribute's unique value, whether it is able to define something that is unique, you have to tell that properly. So yeah, the idea is any set of attribute which is independently and minimally able to functionally define all the other attribute, they are called candidate key. Again, you guys have any session after
Can even
this?
say that can be like likely to become a primary key.
Correct. That's why we call candidate key, because one of them can be made to be a primary key. If I have multiple candidate key in a table, then I can take any one of them and say that okay, this one is the primary key. Okay? That is my choice. So basically, any candidate key is a deserving candidate for becoming a primary key. Any set of attributes which are minimal and can functionally define all other attributes. Do you guys have any session after this?
Yes, sir.
Yes, sir.
From what? 9 o'clock, right? Or 8 o'clock?
No, from 8 o'clock.
8, sir.
Okay. So, anyways, maybe if you guys are not comfortable with week 5, I will request you guys to see this session or maybe some other live session of week 6 later, because this week is very important with respect to your future exams. Okay, because many questions will come from week 5 and week 6. Any set of attributes which are minimal and can functionally define all other attributes of a table are called candidate keys. Now, why do we say minimal? Because I think someone said that it is any, I mean, something like it is some subset of a super key, like one of you said that, yeah, that is correct, but that is not the definition of candidate key. That is one of the property. So it is that property is, there is minimal. This word will define that idea. Minimal means what? So if I have, let's say, AB, which can basically functionally define all other attributes. So basically, let's say I have A, B, C, D, E. We have 5 attributes in a table, and AB being a group of attribute, it can define both. AB will obviously be trivially there, and it can also define C, D, and E. Right? Something like this is happening in a table. But then again, I can say that A is also such that A itself can define ABCD, all the ABCD up to E. Okay, all of them, A can also define that. So then if that is the case, then AB is a super key, because even if I remove B, A individually is able to define all of them, functionally define all of them. So the closure set of A will anyway have ABCD. So this is the closure set of A. Right? But closure set of B will again obviously have ABCD, because A itself is able to do that. So if I add another term with here, another term with A, that will anyway trivially, I mean, it will define all other terms, right? So therefore, this is a super key. That means I can further reduce it. I can prune a few of attributes from a super key, and still I can get such a combination of attribute that can still define or functionally define all other attributes. So from a super key, I can prune a few attributes here and there, and I can still get an attribute set or an individual attribute also, basically, that can individually be able to define all the other attributes as well. But now I cannot, if I cannot reduce further, now in this case it is, let's say, A, but let's say in another example, this is not possible. AB is such an attribute that if I remove A or if I remove B, then either A or B individually cannot functionally determine ABCD, all of them, right? If such a situation occurs, then I say that, okay, if I am removing either A from the pair AB or if I remove B from the pair AB, then individually neither A nor B are able to have a complete closure. And that's why I will say that, okay, that means I cannot further reduce AB, and therefore AB itself is a candidate key. It is not a super key. I mean, obviously it is every candidate key is again a super key in itself by definition, but trivially, but then it is a proper candidate key. So therefore the minimal part is very important. Okay, in case of super key, it is not minimal. So what is a super key? Any set of attributes which are able to functionally define all other attributes. Minimal we will not say. Candidate key is minimal. Fine. Okay.
Sir, both resembles the same only, sir. Super key and
both are, sorry, both means
both resembles the same meaning, but minimal is absent in case of
exactly. They do the same task as I said, right? So if I have this AB example I gave, so let us say A also has the closure. So A also closure determines A, B, C, D, E, as I said. So A itself is able to do that. But then I say, what is AB? So if I ask you what is AB, then you can say AB is a super key. Why? Because A is a key. A itself can determine all the other functional attributes, all the other attributes by having functional dependency with each of them. So A can manage on itself. Alone it can manage that. But if I'm adding some other attribute and then say that, okay, then what is this set of attribute? So you can say that it is a super key, because it is a superset, subset, superset, those things, right? So it is a superset of the candidate key. So that's why we call it super key. But candidate key must be minimal. That means you cannot further reduce it. Okay, but please be aware of this fact that it does not mean it always have to be an atomic attribute or a single attribute. In this example, we are only having A. But as I told, there can be such situation where, let's say, AB itself as a joint can only perform as a candidate key. If you remove either A from this pair or B from this pair, then it might so happen that it is not able to individually determine all other attribute. Neither A can individually determine all other attribute, nor B can individually determine all other attribute. So in such a situation, AB itself is irreducible. You cannot reduce AB further. So then AB itself is a candidate key. So it's not like that every time a single attribute will be able to determine all other attributes. Sometimes you need to have pairs, or even sometimes you need to have 3-4 attributes together to determine all other attribute. So then we will say that it is minimal because we cannot further reduce it and still get all the attributes in closure set. So therefore then such a set of attribute is a candidate key. Okay, fine. So yeah, so candidate key and super key is done. Now 2NF is saying, now let us coming to the 2NF ID, definition. This is not 2NF, yeah. Okay, another important part is any attribute which is present inside a candidate key is called a prime attribute. So what is a prime attribute? Part of
Number of candidate key.
Yeah, part of candidate key. So let's say I have a table T1. In this table T1, I have one candidate key, let's say A, another candidate key, let's say C, another candidate key, let's say E, and can I have like this? Can I have this candidate key? So T1 tables candidate key. Can I have these 3 candidate keys together?
No, sir.
Yes.
Okay. So yeah, we cannot have, because then EC is a super key, because if A is a candidate key, C is a candidate key, then how can I say that EC is again a candidate key? Because C already is a candidate key. I don't need E to, I mean add any value, right? E is not working anything. C itself is able to determine all of them. So therefore EC is a super key. EC is not a candidate key. So EC cannot be a candidate key. But let's say I have another candidate key, B and E. This I can have. I can have a table in which A individually can serve as a candidate key, C individually can serve as a candidate key, and B and E together they can serve as a candidate key. Okay, so if you remove B or E, either one of them from the pair, then they will no longer work as candidate key. They will no longer be able to determine all the attributes. But if you keep B and E together, then functionally they can determine all the attributes. Right? So candidate key of T1 can be like this. Fine. So if this is the scenario and we have, let's say the table is T1 is basically A, B, C, D, E. So this is my table, A, B, C, D, E. Okay. So then what are the prime attributes? The prime attributes are
A, B, C, E.
correct. A, B, C, and E. All of these attributes are prime attributes. So because these are the part of the candidate keys. So only D in the table is a non-prime attribute.
Excuse me, sir.
Yeah.
Sir, but how the BE will be the candidate key? Because we are the statement is like that candidate key should be with the minimal number of attributes, right? So
Correct.
BE will not be the candidate key.
I
So in
just
that
told
case,
it might so happen that it's not always that you have only one character in a candidate key. It might not be the situation. You can have more than one character in the candidate key when we will see an example, you will understand. So when that might happen, when B individually cannot determine a candidate key, E individually cannot determine, B individually cannot determine all attribute, E individually cannot determine all attribute. But if you club together B and E, then they can determine all attribute. There is
yes,
no
that,
so
yes,
there is
sir,
no.
I got that. I got that. But
Okay,
if we collecting a set for a candidate key, in that case, if A and C are the our purpose is solve with A and C, then how come we include BE in the candidate key list? That's my question.
okay, yeah, so that
Mm.
is a understanding problem. The thing is, we do not put any condition on if I have one character candidate key, then I don't need 2 or 3 character candidate key. It's not like that. That happens for
Okay,
primary key. Okay.
okay, okay,
Why,
okay.
sir, D is not a primary key, primary attribute, and what is the one shot of prime attribute?
There is prime attribute and primary key are 2 different things. Prime attribute is part of candidate key. Primary key is any one of the candidate key itself. You pick a particular candidate key and say that this is the primary key. That is completely different. Prime attribute is all those attributes which are part of any one of the candidate key. So like in this example, A, C, B, E, A is a candidate key, C is a candidate key, B, E together is a candidate key, right? So now I will say since A attribute, C attribute, B attribute and E attribute, they are either a candidate key in themselves or they are part of one of the candidate key. Therefore, each of these attributes are prime attributes. Primary key is something completely different. Primary key is, I have these three candidate key in a table. I choose any one of them and say that I nominate this candidate key to work as a primary key. So then let's say I say that BE is a primary key. So the BE complete thing will be a primary key. This is not prime attribute, that is primary key, a completely separate concept. Okay. Okay, fine. So I think so the one who was asking the previous doubt that how can we have B is candidate key, is that okay? Is that understood?
Yes, sir. Now I got it. Sir, my actually the impression that I have was wrong. I thought
Aha.
candidate key will also, if we have A and C, then we will not search again, or any member will not be the part of candidate key. But it is not like that. We can have as much as group possible, which will be the minimal and can discover all the attributes.
Correct, correct,
Yeah,
exactly.
got it now. Yeah, got
Yeah.
it now. Thank you, sir.
Yeah, yeah. So now let us go into 2NF. We have understood what are primary attributes and what are candidate keys. Just for the sake of mentioning, I am saying this. In the whole discussion of this normalization and our DBMS further weeks, primary key का काम जो होना था हो गया. You guys have done whatever SQL query writing on the basis of primary key and all. Now we will not discuss primary key. We will always discuss candidate key. Why? Because database design is based upon the data relationships that you have in a table, right? Now primary key is just a nominated candidate among all the candidate key. Each and every candidate key internally does the same work, can do the same work that the primary key is doing, because primary key is just one of the candidate. It has no extra features from the other candidate keys, from its siblings, right? It does not have any extra feature. It's just we choose any one of the field to be, any one of the candidate key to serve as a primary key. So therefore, in order to let's say incorporate the nuances that occurs because of the patterns in data, because of because of these related patterns in data, that can only be catered to when you are incorporating all the candidate keys together in our design process, right? Only primary key is just one of the example of candidate keys. So you need to talk about candidate keys always. So don't get confused. Whatever we will talk about in the future discussion, it will be always based upon candidate key and never on primary key. Okay, prime attribute is something completely different. Prime attribute is a part of candidate key. Fine. So now let us discuss what is 2NF. 2NF says that a table, this is checking rule. Again, our main structure is known, right? We will have some checking rule and then conversion rule. So the checking rule is a table, if okay, a table is in 2NF when there are no such functional dependency applicable on the table where a where a prime attribute functionally determines a non-prime attribute.
Sir, can we get PDF of this, sir?
Fine. I will. Anyways, these are already talked about in the slides in lecture, but still I will give, no problem. But then I will not delete. I will keep that in mind. I will write in the next page. Okay, fine. So a table is in 2NF when there are no such functional dependency applicable on the table where a prime attribute functionally determines a non-prime attribute. Okay, now what does this mean? So this means that you will have no such functional. So our table is given. Now on that table you will have, just a second, yeah. On that table you will have some applicable functional dependencies, right? Any table will have functional dependencies on that. Now, in order to check whether the given table T1, whether it is in 2NF or not, you have to go through all the functional dependencies of T1. So go through all FDs of T1, fine, and check this condition. A prime attribute functionally determines a non-prime attribute. If such a functional dependency exists, then we will say that it is not in 2NF. The table is not in 2NF. So let's take an example and see what do we mean by that. So let's take an example of a table T, okay, where the functional dependencies are PQ goes to R and Q goes to S. This is a famous example. I think it came in GATE 1 year. Fine. So tell me the candidate keys. So what is step 1? First of all, what do we have to do? Go through all FDs of T1 and check whether a prime attribute determines a non-prime attribute or not. Now we know prime attributes are nothing but parts of candidate key. So in order to find which are the prime attribute in these functional dependencies, right? In these in these two functional dependencies, we need to find out what are the candidate keys of the table. Once we find the candidate keys, then we will have the prime attribute, and then we will see whether the condition is there or not. So what are the candidate keys?
PQ.
PQ. Are you sure? Okay, fine. So why PQ? Because the step to find candidate key is we will see what is there, what is not there on the right hand side. So right hand side means we will check all the functional dependency and see which attributes are not there in the right hand side. These are all week 5 topics, you should cover it, but I'm just repeating. So on right hand side of this functional dependency we have S, and on this functional dependency we have R. So R and S we will see later. Other than R and S, what are the attributes in this table? So we see that P and Q, right? So P and Q must be there in the candidate key, because if I do not include P and Q in the candidate key, there is no other way I can derive P and Q. And our main aim of finding a candidate key is it should be able to derive all the attribute. So because P and Q is not there on the right hand side, therefore I will not have any way to derive P and Q if I do not include P and Q in the candidate key itself. If I include P and Q in the candidate key itself, then obviously trivially it will define P and Q. Its own self it will define. So therefore I am getting P and Q. Now I will see what are the other attributes I ignored, which are already there on the right hand side. So S and R are there. So I will check whatever I have in hand, which I compulsorily need to include, which are P and Q. Can I derive the other two attributes R and S using P and Q or not? So I am checking that if I have P and Q together, then according to this functional dependency, I can derive R. And then again, according to this functional dependency, Q is already in my hand. So I can take Q and derive S. So therefore, PQ plus is PQRS. Right? So therefore, PQ is a candidate key. So this is your step 1. Find candidate keys. I have written this S here. It is very important. Why? Because you are trying to find the prime attribute. That is your ultimate goal. So if you want to find prime attribute, you need to find all the all the candidate keys, right? Because only one candidate key will not, some other candidate key might also be there. And if you do not consider that, then you will not have the prime attribute corresponding to that candidate key. We will see some example. It will be clear. Anyways, so in this example, candidate key is PQ. Okay. Then what are the prime attributes?
P and Q.
Okay.
P and Q.
Correct. So step 2, prime attribute P and Q. What was the condition? A prime attribute functionally determines a non-prime attribute. If such a table is, if such a functional dependency is there in the table, then we will say it is not in 2NF, right? We told you that there should be no such functional dependency where a prime attribute functionally determines a non-prime attribute. So what happens in this table? Is there such a functional dependency?
Yes, sir. Q
Q
determines.
determines S.
Correct.
Determines PQ determines R as well.
Because non-prime attribute is what in this case PQ to chala gaya, so R and S are non-prime attribute. So we have this Q determines S as a problematic situation. PQ is a candidate key itself, so it will anyway determine, that is fine. So this functional dependency I have no trouble with. But then Q is a part, right? The trouble is with having partial. So that's why, what is the problem happening over here? If a part of a candidate key determines a non-prime attribute. So whenever some part of a candidate key itself individually determines a particular non-prime attribute, then I am saying it is the rule that you have to, it is problematic basically, it is not in 2NF. So since this dependency is happening when a part of a candidate key does some naughty work, does some mischief, therefore the mischief in this case is basically determining a non-prime attribute. So when a part of a candidate key is working like this, we are having trouble. Therefore this dependency, let me write it in another color. So therefore this dependency, which is satisfying this condition that we discussed, is called partial dependency. So why do we call it partial dependency? Because a part of a candidate key is causing us this trouble, therefore it is called partial dependency. Okay, fine. So now our checking rules are over, that this is the reason it is no longer, it is not in 2NF. So since partial dependency is present, I will write, since partial dependency is present, therefore T1 is not in second normal form. By the way, is T1 not T1, T, right? Yeah. So by the way, is T in 1NF or not? Any idea?
Yes, sir, it is.
Yeah. But it is in 1NF. Why? I told you there should not be any multi-valued attribute, right? And whenever, assume this thing, this is one rule actually, not rule, this is something convention. Whenever a table definition is given to you in the form of functional dependencies and attributes, so basically if I am telling you that the table is T, A, B, C, D, and the associated functional dependency set is A goes to something, C, B, C, B, D goes to A, whatever, right? Something like this, dot, dot, dot. If I am giving you the table definition in this manner, then consider all the attributes are atomic attributes. Okay. And in the question, if a statement like question is given to you where it is saying that, where it will be explicitly mentioned that this attribute is multi-valued attribute, then so it is already mentioned. So you have to take care of that accordingly. But if the table definition is given to you in terms of functional dependencies, then implicitly consider it that it is already in first normal form. Okay, I think that is also clear. Okay. So partial dependency we learned, and then we saw that.
So this partial dependency concept.
What happened? Says
partial dependency a little bit.
I discussed, no? Just maybe rewatch it because I have to cover some topics. So maybe rewatch it, you will understand. I discussed in very shortly. Yeah, someone else was also asking something. Go ahead. No one? Okay, fine. So, okay, so the partial dependency part is over. Again, just repeating one more time. The thing is, if a part of a candidate key, if a part attribute of a candidate key functionally determines a non-prime attribute of the table, then we call it as a partial dependency. Now here Q is a prime attribute and S is a non-prime attribute. Therefore, if Q is determining S, then such a functional dependency is called partial dependency. And if such a functional dependency exists in a table, we will say that table is not in 2NF. Not in 2NF. Okay, remember this, it is not in 2NF. Okay, briefly seeing why this is the case. Why, I mean, ye to ho gaya, we have mentioned some rules, but why these rules came into existence, if we just try to look at it a little bit deeper way or fundamental way, let us take three values ABC. Okay, I'm not taking the PQRS example, just take three random columns. Okay, and let us say A, let me just give me some time, let me just frame it, you will see that why this is occurring. Let's say C1, C2. For A1, it is repeating. B1, no, sorry, B2, right? And then A2, E2, C2. Just a second, sorry. Let it be C3. Okay. So tell me in this table, what are the functional dependencies?
AB determines C.
Can I write A determines C?
No, because of first two rows.
B determines C.
Fine. Then row 1 and row 2, A1 is there, but C1, C2 is there. Therefore, A goes to C, I cannot write. Can I write B determines C? Yes. Right? You can see that every time B is getting repetition, C is getting repetition. Now, can I write AB determines C? Obviously, trivially satisfied. Right. Now, there is one other thing. Now you might ask that why AB, I mean, I will not consider AB determining C because this is something trivially I am adding. Let us add another attribute and then you will understand why AB is important. Right. So let's say B2 is there, right? So whenever B2 is there, let's say D2, D3. Okay. Let us, for the sake of simplicity, let us keep it like this. Okay. Now, okay. Anyways, fine. But if I take this B over here, A1, B1 is repeated somewhere. A2, B2, A2, B2, A2, B1, A1, B3, A2, B3. Anyway, all the entries are unique, I think. So A2, A2, B2, B3, B1, B2, A1, B1, B2, B3, A2, B2. Okay, no, yeah, here also it is not critical. Fine. Yeah. So let's say if this is the situation, right? So then AB goes to C, AB function determines C is there. But then I ask you the question, what is the candidate key of this table? Let us say this is not yet asked. Can someone tell me what is the candidate key of this table?
ABC.
BC is the
AG.
candidate.
So BC cannot be because of first and last row.
Correct. So then
ABC.
ABC?
Yes, sir.
ABC. Okay. So why do we need C over here? Can AB work as a candidate key? I think one of you said AB, right?
It can
Sir,
work
I think
because there are no like
AB.
repetitions or something.
Correct. So there are
Yes,
no
sir, it
repetition of AB. Yeah. So AB can serve as a candidate key. I don't need C. So AB is a candidate key. Done. Okay. So AB is a candidate key. So since AB is candidate key and B goes to B function determines C, I can have, yes, B is actually function determining C. So this is a classic example of a situation where a prime attribute, B is the prime attribute. So a prime attribute B is functionally determining a non-prime attribute C. If C would have been a part of candidate key, ABC would have been a candidate key, then C would also have been a prime attribute, and then I don't have a trouble. If a prime attribute is functionally determining another prime attribute, so if I have some prime attribute, arrow prime attribute, then I do not have any trouble. The only thing is if a prime attribute is determining a non-prime attribute, right? So here C is a non-prime attribute. So that is not allowed. That is what we call a partial dependency.
Sir, over here AC is also candidate key.
AC is getting repeated. Okay, sorry, not getting repeated. Wait,
Yes.
let me see. A1, C1, C2, that might happen. I'm just devising on the run, right? So it might happen. Let me check. A2, C2. A2, C3, A2, C1. Yeah, so A1, C1, C2, A2, A2, C2, C3. Got it. Okay, so let me just make one change somewhere. Wait.
So we got the concept, so we can just.
You got the idea, right? But the thing
Yes.
is still let us, because I have to see I need to show another concept. That's why I need to make a good example. If I change this, then B will also have to be changed. Okay, now wait, let us then I cannot do. Yeah, it will take some time to think. I will not. I mean, within this much entry, I have to add entries over here. Then I think it will be better. Fine. So in this example, although it is not satisfying, AC is also a candidate key. So C again will be a prime attribute. Okay. So if I take A2C2, A2C2, right?
So the
Yeah.
problem is AB is already a candidate key, so it has to uniquely determine C. So you cannot make any change over there in C.
I can by adding another value for B and A, that I can do, but it will take again some three, four more entries that I don't want to take. It will take time. Anyways, so let us for the time being, let us focus on one point. And as of now, yeah, so you are correct. AC is also a candidate key over here in the according to this example. But let us observe one another part. Assume as of now that C is a non-prime attribute. I mean, I have not considered AC being a candidate key. I have not considered that, but yeah, in this particular example, AC is also a candidate key and C is also a prime attribute, strictly speaking on the data. But assume as of now, let's say there are some other data also, right? Some other data also, and according to those data, maybe it is not a. Oh, wait. I can make it in another way, right? Just a second. A1C3 is there, right? If I, let's say, repeat this, let me make it, just a second. A2, B2, C2, A2, B2, C2, D3, let's say
So the
D4.
problem is then A2 B2 will not be I mean AB will
Candidate
not
key.
be a candidate.
Wait, K2, B2 is repeated. Then again, this cannot be. If I change this, then again it will be the same entry. Yeah. So I have to add some value. Otherwise, it is a bit difficult now. Correct. Anyway, so what I was talking about is, let us keep it like this only. What was the previous value here? C2. So you see, if you see this table, as of now, just see this table. AB is a candidate key, and B determines C was a partial dependency. Now, why is this partial dependency causing redundancy? That was the main point that I wanted to show. You see, whenever B is automatically determining C, right? Whenever B is automatically determining C, if you look from the perspective of ABC and AB being the candidate key only, okay, AC is also candidate key, forget about that as of now. But if you see that AB being a candidate key, right, a part of the candidate key is determining another attribute C, correct? So what is that? You can see that whenever B is,
So pardon me, sir. I think AB is not a candidate key because of row number 3 and last row.
I think I made a change, right? A2, B2,
Yeah, it
Okay,
was
sorry, you might have
not
changed
B2.
something.
It was, I think, B3
Sir,
or
no issue, sir.
D1.
We can proceed.
If I make it D, then the row will be repeated anyways.
Yeah, D3 then.
Correct. Then the row
Sir,
will be.
somewhere in the first 3 column you have made some change, sir, because the D was correct, D6. Or maybe you have added another row, sir. Maybe because of that. You can delete the last row, sir.
The
Sir,
values are
last
kept.
row, sir,
Sorry,
last row is B1, C1, sir.
Sorry, D1, C1 was there.
Yes, sir.
I changed it later, na? Wait, A2, B1, A2, B1 is there again. A2, B1, A2, B1, A2, B1, A2, B1 is not there. Then I think it will be fine. Yeah. So A2, B1, C1, D6, right? So if this is the case, then again, then it is okay. But anyways, now coming back to that discussion. So if I have this A2, I mean, if I have AB being the candidate key, so then you see that whenever B is there, C is already repeating. Whenever B2, C2, B2, C2. So this C2 entry will be repeating every time B2 is happening, right? Again, if some point I have B2, then again C2 will be there, irrespective of A. I am not even looking at A. I am looking at B2 and I'm looking at B, and on the basis of that C is getting determined. But then again, my candidate key is AB. So it is like, I mean, you can determine C on the basis of B itself. Why do you need a candidate key separately to determine C? Because the idea of candidate keys will determine all the attributes individually, no problem. But if you have such a dependency where the part of the candidate key is again individually determining another non-prime attribute, right? I mean, non-prime means basically it has nothing to do with the candidate key, something like that, you assume. So determining, then you don't need the whole candidate key to determine that non-prime attribute, right? A part of it is able to determine it. So therefore, this is the redundancy. You see, every time I told you multiple entry is nothing but redundancy. So you have this multiple entry coming, and that is still okay if that entry is coming with respect to AB being a pair together. Are you getting what I mean? So if AB, if only C is getting repeated when AB together is getting repeated. So let's say here A1, B2 is there. Now here A2, B2 is there. A2, B2 is as a pair, A2, B2 is different. A1, B2 and A2, B2 are not equal. They are not equal, right? So since they are not equal, then this C2, C2, I mean, even if this C2, C2 wouldn't have been there, something else would have been there. Let's say C2, C3 would have been there. Then also I wouldn't have been into any trouble. But then again, if that was the case, if let's say C2, C3 was there, okay. So then I can say that, okay, AB is not repeated because AB is the candidate key. Now AB is a complete candidate key. It is not getting repeated. I mean, both A and B together, I mean, as a pair. Since it is not getting repeated, therefore C is also different, and therefore AB functionally determines C. Now this is not redundancy because this is a new information. This is your let's say information 1. This is your information 2. I mean, I'm saying these two pairs as information. So information 1, information 2. These are two new information, and this is also two new information. Information 3, information 4. So information 1 and information 3 are corresponding to each other, and information 2 and information 4 are mapped to I mean, these are the pairs of information. Basically, what I mean is these are the functional dependencies. Now, but if I have this previous case where C was partially determined by B, then I have this C2. Now you tell me, is it still, are the information labels still holding? I1, I2 is still new, right? I1,
Can I ask?
just a second. So I1 and I2 are still different information because as a pair A1, B2 and A2, B2 are different entries. As a pair, they are different. So I1 and I2 are still unique. Two are different. But although both of these, I mean, these two informations are different, but these two information are no longer different. I3 and I4 are the same values, C2, C2. And also that is also happening that some intermediate field, I mean, some not intermediate, a partial field is able to figure out this repetition in value. This information, the C values are getting repeated on the basis of repetition in B value itself. So this is a redundancy. Why redundancy? Because I was able to figure out the repetition of C on the basis of B attribute itself, but I am using both the AB attribute together. So that's why this is something redundant work we are doing. We are not doing it in a minimal way. And that's why this is where the redundancy comes from. If you have partial dependency, I mean, in the data set, this is how it looks. By you don't have to know the data set, right? Here we did not know the data set, but we figured out the partial dependency by following the rules. But why the redundancy comes because of partial dependency, that you can see over here. Every time B is getting repeated, B3, B3, C3, C3, B1, B1, C1, C1, right? But then what is the job of A then? I am taking AB as a candidate key. Then what is A doing? I mean, in terms of defining C. In terms of defining B, it is fine. But defining C, what is A doing? Nothing. So that is the redundancy that we are talking about. Why the work of A is non-existent over here. B itself can do it. So because in order to remove this redundancy, what can we do? I mean, I will come to your question, but let me address this now. In order to remove this redundancy, simple. B is able to determine C on its own, right? Just leave B and C together. I mean, let them go away. That's what it is. I mean, we will make B and C move out of the table. So they can do their work on their own. So they will move out. So what do we do now? So this is where the applications, I will come to the previous example, but with respect to this example, let me discuss it once first. So what to do to remove, the redundancy? So the answer is remove the partial dependency. I mean, the reason of redundancy, right? So remove the partial dependency. How can we remove the partial dependency? What is partial dependency in this case? In this case, partial dependency is B goes to C. So this is your partial dependency. Okay. So now how will we basically remove it? I said that I will separate it out. Now you guys have learned the lossless decomposition, right? We will have a intersecting field between the two decomposed table, and that intersecting field must be a primary key in one of the tables. Then we will have a lossless decomposition. So if that is the case, what I will do is I will separate out B and C together by finding B plus. There might be some other attributes of that B might be determining, right? I'm not sure. In this example, only C is there, but let us say some other attributes might also be there. So the algorithm is saying that your step one is, so let me write it in a different manner since you guys wanted the PDF. So what to do is we will, yeah, go ahead, say.
Sir, the C3, when C3 was there, then B and C was not partial, that is decomposed, no?
Yeah. When C3 was there, then it was not partial. Let's take now.
C2 is interchanged to C3, then B and C is not like partial dependence, no? If the values of B, in the value of A pair, B pair, and C pair. We are
Okay.
comparing B and C pair when we have interchanged to the information number 2. Then this value, if we interchange with C2 to C3 at the second information,
Okay. Huh?
then this value is not like partial dependence. Na?
No, no,
B
no.
and C is not.
Then no, 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 no. Obviously no, because if I have B2 here, partial dependency will only happen when C is also repeating. C2 must be there, right? So then only partial dependency. Yeah, someone else was also asking something. Go ahead. I mean, whatever you said is right. That's what I mean. So yeah, if it is C3, then it is no longer a partial dependency. So that's what I said, that if it is C3, then there is no partial dependency because there is no redundancy. Here only we have redundancy, because why the redundancy? B2 is getting repeated, C2 is also getting repeated. Now that repetition is still okay. Repetition will anyway happen. You might say repetition will happen anyway for, I mean, whenever I have the primary key repeated, I'm sorry, not the primary key, the candidate key repeated, then also the other fields will repeat. That is the definition of candidate key.
Candidate key is not ABC, AB only.
Correct,
Why?
correct, correct. C, I mean, so I told you na, that in this example, C, let us assume that C is not the candidate key, because I mean, I have to then add 3-4 more rows, then only I can show you. As of now, let us say that AB is the candidate key. If you follow this particular value, or AC is the candidate key. Either AB can be a candidate key or AC can be a candidate key. Okay, now if you say ABC, that is not a candidate key. Why? Because AB itself can determine C. Then why do I need ABC together as the candidate key? These are, I mean, week 3 concepts. Okay, I think you please watch the week 3 talk. AC is a candidate key in itself. That is fine. That I agree. But that in order to remove that idea, I have to add some more rows that I don't want to do now. But if you say ABC, you want to compose all 3 attributes together, that is not required. AB is a candidate key on its own. AC can serve as a candidate key on its own. I don't need ABC together to make one composite 3 attribute candidate key.
As well as the minimal concept is also there, no?
Yeah, that's why. Okay, so yeah, so how do? We will remove the partial dependency. How do we remove the partial dependency? By making a lossless decomposition. How do we do lossless decomposition? So by lossless decomposition, remove partial dependency. How to do that? Step 1 is closure of the prime attribute. What is the prime attribute? Tell fast. What is the prime attribute? B, right? So B plus is B and C in this case.
Yes.
Right? Can I write D over here? Is D there in the closure of B?
No.
No, correct. So only B and C are there, right? So whatever is the closure set of B, we will take and separate that out. So
over here we are considering AB as the candidate key or just B?
why B is candidate key? AB is candidate key, right? I have written.
So then we are finding the closure of the prime attribute, that is B. Then
Correct,
why not
correct.
A, sir?
That is the rule, man. If you want to separate out, right? This is the rule.
Okay. We are separating. Okay.
By lossless decomposition, we will remove the partial dependency. So we will find the closure of the prime attribute. Why? And this is not also rule. This is like, if you observe it, you will understand. The problem is with this partial dependency. Partial dependency is B determines C. Now I want to separate this B determines C out of the table. So whose closure we will find? What has A has to do here? Right. So you will need to separate B, C together. So I need to find the prime closure set of B, so that I can figure out what are the attributes that B is determining, and I can bundle them up and put them into one table. That's what we are going to do. Right. But you can remember it as a rule, you can remember it as a common sense kind of stuff, whatever. I mean, basically the rule is you find the closure of the prime attribute, which is BC. Now you separate out that into a separate table. So my T2 as a new table I will create with the closure set of B. So my new table will be what? B and C. And my initial table was what? The T table. This is T, right? This is T, suppose T1. So my T1 table is
AD.
A, B, and D. Okay. So my T1 table is A, B, and D. Is this a lossless decomposition?
Yes.
Why? Why?
Because B is common to both, and B is the primary key in T2.
Correct. So this is how, now if I say that, okay, BC and ABD are the two tables that we got. Now let us quickly apply the functional dependencies that we initially had. So B determines C was there under this table. I mean, will be there under this table. In this table, I will have what? A determines C is not a functional, I mean, C is not there anymore.
So AB determines D.
Correct. Now tell me, is there any functional dependency where the prime attribute is determining non-prime attribute? No. Why? Because in this table only one FD is there and there B is the primary key. In this table also one FD is there, here AB is the primary key. So therefore, I have decomposed the table T1 into two tables. Let's say now call it T1 dash. T1 dash which is ABD and T2 which is BC. Now this decomposed table does not have any partial dependency because no dependencies in each of the table have this prime attribute determining a non-prime attribute feature. So therefore, this is a, now I will so since we have got this new two tables, right? Again, we will apply the checking conditions. So apply, reapply the checking rules to see whether the new tables are in second normal form or not. So again, that's what I said. If you apply the again the same condition of checking whether a table is in 2NF or not, so basically you will see the what are the candidate keys and you will see the prime attribute. So what is the candidate key in table T2? In this table,
B.
Candidate key is B. In this table, candidate key is AB, and there are no other candidate key. Now, as you can see, only one functional dependency is there, and that is not prime attribute or anything like that. So basically, this table is in 2NF. So now you have reached 2NF. Okay, applying the same logic in our actual example now. Let me draw a line here.
The new two table is having only D column.
Both the table will have B column, right? Because otherwise we have to share a column in order to have a lossless decomposition.
Both
Okay.
tables have only,
both the tables must have an intersecting or common attribute or common column, which is B in this case, because if you do not have that, then you will not have lossless decomposition. Okay, now what is lossless decomposition? Refer week 5, it will be clear. Okay. So anyway, so we have done this. This is another example. Now coming back to our previous example, which was that, okay, we figured out that PQR and Q determines says this table was not in 2NF. So since partial dependency is present, therefore T is not in 2NF. But it is in 1NF because I told you that if I give you table definition in this manner using dependencies, then it is conventionally it is assumed that it is in 1NF, right? Unless it is specifically mentioned that one of the attribute is multi-valued. Okay. So now what we have to do, here we saw the checking condition. Now tell me the steps.
So we'll have to find the.
What do we have to find?
So we have to remove the partial dependency first.
So for that, what do we do?
Closure of prime attribute.
Correct. What is the prime attribute in this example?
Q. Q is the attribute
Q.
which is giving trouble.
Correct. So Q is the attribute which is giving trouble. So Q plus, which is
QS.
QS.
great. So we will separate out this QS together, right? So step 2 is dividing the table. So my T 1 dash will be something.
PQR.
Yeah, T2 will be something. So I am separating QNS into TQ. So QNS will be here. Q will be common, right? Because I need a common attribute for lossless, and other ones are P and R. Okay. So is it lossless? Yeah, because let us apply the functional dependencies now. The FD set of this will be what?
Q
Q
determines S.
Correct. And here?
PQ determines R.
Correct. So you can see that obviously here the candidate key is PQ, here the candidate key is Q. So there is no question of prime attribute because there are no other FDs applicable. So now therefore this new set of table T1 dash and T2, both of them are in 2NF. Fine. You reapply the checking condition on T1 dash and T2 again, which is basically checking whether there are prime attribute prime attribute determining non-prime attribute. You see there is no such thing. So now you can say that okay. So therefore these are in 2NF. Yeah. So that was the how we convert. Let us take a little bit more involved example, and then we will move to 3NF. It's already 8 o'clock. Anyways, watch this session or maybe some other previously recorded live session, anyone, whether you prefer, whichever you prefer, but watch this because this week is very important. I mean, the recording part, I mean. Let us take another example, and that is, let's say, the table is and the functional dependency set is P goes to Q, right? Q goes to P, and R goes to S. Okay, fine. We will do a little bit speed now. Okay, candidate keys. Anyone?
PQR.
PR.
PR. S.
Why S, T and Q? So S, T and Q. PR we have to include. PR से हम लोग क्या find कर सकते हैं? What do we find using P and R? P goes to Q. Okay, Q goes to P. Yeah. R goes to S. So PR means PQ, RST, PQ, RST, all are covered, right? So PR can figure out everything. Any other candidate key?
No, sir, because only P and R are on the LHS. Remaining
Correct.
R and RHS.
Correct. So prime attribute P and R. Okay. Now we will check partial dependency. Okay. Now many partial dependencies, right?
R to S.
So
P
P
to
goes
Q.
to P to Q is also partial, right?
Yes.
Yes.
Okay. Then another R to S.
R to S.
Two partial dependencies we got. Okay. So now what to do? Remove one of them. I mean, we will do one by one. So first remove, let's say the first one, which is PQ. Okay. How to do that? P plus, right? So which is P, Q, T. Correct? So now I will remove PQT together. I mean, club PQT together and remove it. So my new table would be, so this is, let's say, step 1. My step 2 will be, let's say, some T2 table. This is, let's say, T table, right? So let's T1 table. So T1 table will be P, Q, and T. T2 table will be, I have taken this P thing. Let's take P as common. Okay, so P common will be there. And what are the leftover things?
R and S.
P, R, and S. Fine. So that is done. Now apply the functional dependencies. What are the functional dependencies? On first table, P goes
P
to
gives
Qt,
P gives to
right? And why, by the way, this is understood, right? Because we have this PQT closure is there, and here I have this PQT, so P goes to Qt will happen. Then what are the other things, other functional dependencies over here? Even if you derive using this, right? P goes to Q, Q goes to T, so you can have P goes to Qt. I mean, I'm just clubbing both of them together. Okay, what are the other functional dependencies? Q goes to T.
yes.
Anything else?
No, sir.
Okay, now come to the table 2.
R gives S.
P is also there, right?
But P does not determine anything else, sir, in that table.
P does not determine anything.
Yes, sir, in T2.
Sure?
Yes, sir.
Correct. So P R goes to S is the only dependency. Okay. Now in T1, we removed PQ by doing what? I mean, we have this PQ thing. So how did we remove it? Partial dependency. Just a second. So yeah, prime attributes were which one? Yeah, P and R were the prime attributes. So R goes to S and P goes to Q are the two dependencies which are problematic. In order to remove PQ, we defined P plus, and P plus we got PQT. So we will remove PQT club together and remove them separately. So we have this PQT, and the obviously P goes to QT is there. Therefore, it is lossless decomposition. No problem. P is the common attribute. So in T2 table also we don't worry about anything, because in one of the table it must be lossless. I mean, it must be a key. So since P goes to Qt is the key over in T1, therefore I will not worry about what's happening in T2. So these are weak 5 things again I'm saying. So now tell me, at this situation, is T1 in second normal form or not?
Yes, sir, it is.
It is in second normal form?
Yes, yes.
Correct. Right? Why? Because there is one at function dependency Q determines T, the second one.
Yeah.
But what is Q? Q is a non-prime. Correct. So Q is non-prime. What is T? T is also non-prime. Non-prime pointing to function determining non-prime, I am not worried. Okay, because P is the prime attribute and P is the primary key. So if there is no trouble, it is atomic. Okay, done. So T1 is in second normal form. Fine. What about T2?
Non-prime determines non-prime. Again, 2NF.
Right. So you have this R and S. R is a, I mean, key prime. No, R is not non-prime, right? R is prime attribute. So
Sir,
you have
prime attributes has to be part of some of the candidate. Okay, yes, yes, correct. My mistake, sir. My mistake.
Right. So therefore, so this is where you have to pay attention, and that's why I said that week 6 is very important, because you might make very simple mistakes. Okay. So
R is
what
the
is
candidate key.
Yeah, so follow the process, it is better. What is the process? Once we do the decomposition, again I'm restating, once we do the decomposition, till this point it was okay, right? We saw that P goes to PQT, we separated PQT together, we kept the P value common between T1 and T2 because of lossless that thing. This is fine. After that, what we will do, we will apply the checking conditions again, whether each table is in 2NF or not, separately. That is, I will apply on T1 also, then again separately I will apply on T2 also, that whether each of them are in 2NF or not. So first of all, I am applying on T1, because what are the, and before doing that, I need to figure out what are the functional dependency applicable on P1. So you see, P goes to Q, Q goes to T, so P goes to Qt, Q goes to T, obviously it will be there. So these are the two functional dependency from the primary functional dependency set that I can derive and apply on T1. Okay. You could have also written it like P goes to Q, Q goes to T. I mean, two separate things. Then also same meaning, basically, no difference. Anyways, so these are the dependencies. Now again, first task is figure out the functional dependencies. On T2, we will apply the same logic and figure out the functional dependencies. So R determines S. That is the functional dependency. Any other functional dependency? No, we could not find. right? From the primary set of dependency, there are no applicable dependency in T2 other than R and S. R goes to S. So task one is, after doing the partition, after doing the subdivision of table, task one is figure out the functional dependency in each table. Okay. Figure out FDs in decomposed tables. Okay. Now, once we have done this, then we will see the second thing. So once you have figured out that what are the dependencies, then your step 2 is apply the rules, apply check rules to figure out whether it is 2NF or not. So you found out the dependencies, then applied the checking rules and saw that it is in 2NF. T1's work is done. Now go to T2 and do the same. Figured out the functional dependency, now apply the checking rules. Now you see what are the checking rules. Checking rules is saying whether any prime attribute is determining a non-prime attribute. So in order to check that, you need to figure out what are the prime attributes in T2. In order to figure out that, you need to figure out what are the candidate keys of T2. So what are the candidate keys of T2?
R.
PR.
PR. Why? Because if you do not include P, there is no other functional dependency that can determine P, right? So you need to have P, and P cannot again do anything else. So I will include PR. Is PS also a functional dependency? Sorry, is a candidate key?
No, sir, it has to include R.
Correct. It
It
has to,
won't be minimal then.
right? Okay. So is PS is not there, and RS is obviously not there because it's anyway there. So PR is the candidate key. Now that means my prime attribute is P and R. So what is this? And non-prime attribute is S. So therefore this functional dependency
Partial.
again is problematic. Partial. So my partial dependency, this is again PD. Arey yaar. This is again partial dependency. Okay. So same trick, how to remove it? Step 1.
Closure of R.
RNS, right? Then step 2, T3, RNS, T4, R must be common.
P.
Apply same logic again. First step is what? Figure out the functional dependency after decomposition. So what are the functional dependency on RS? R goes to S. What are the functional dependency on PR?
Nothing.
No functional dependency. That means basically R and PR unrelated two fields joined together. So yeah. So let it be there. R and S is there. Now, so functional dependency figuring out is done. Step 2 is apply checking rules. Is there any prime attribute, non-prime attribute pointing kind of relationship? No. Why? Because only one FD and sufficed. Here there is no functional dependency. We have this random thing, and then there is no point of, there is no constraint. Even if there are some things happening in the data set, I am not worried because the business people have not given me any relation between P and R so as to figure out if this is any problem or not. So I will keep it as it is. So I will say that it is in second normal form.
So in table T4, then R and P both together will become a candidate key. No?
Yeah, so that is trivially candidate key, right? There is no other attribute where it can serve its candidate key purpose because there are only two attributes. So whose candidate key will it become? R and P itself will be its own candidate key. It doesn't make any difference. So basically, since I do not have any partial dependency in T4, T4 is in 2NF, T3 is in 2NF, and therefore, what are the final tables? Tell me.
PQT. T1.
T1,
T3 and T4.
T3, fine. These are the three tables that we get. Okay, and all of them are in second normal form. So I hope now this should be clear of how you can break something down in functional dependencies. Sorry, break a particular table into a second normal form. There is one example for those who want to solve it later. Okay, maybe I will give it in that sheet itself. Okay, so now we will
Excuse
move
me,
to
sir.
the
Excuse me, sir.
tell.
In this previous example, do we have to create a T4 because there is no relation between P and R? So isn't it a redundant information that we have?
So if we do not create T4, what I mean is basically you need to separate RNS, right? Sorry, not RNS. Yeah, RNS, because RNS is a partial dependency. From T2, you need to separate RNS, because if RNS is there inside T2, then it is problematic along with P. So there was somehow I need to separate RNS. So if I separate out RNS, then anyway the leftover terms are P and R. So I'm not creating or anything, it is a leftover term. So therefore, I'm not worried about it. It's not redundancy because, I mean, there is no relation or any constraint that are given to me on the basis of which I will say that this is something happening or some. I mean, there is no information about it. And you're saying, if why are we creating it? Okay, you don't create it. So how can you separate RNS without creating T4? Because if you separate out RNS and make T3 using RNS, then the attribute will be left, right? Some P attribute will be left. You cannot put P attribute in dustbin, because then that will be loss of information. P attribute, maybe it can be some account number field, some important field. So although they are not in any functional dependency kind of relation, but at least you need to preserve that data, because later if you need it, then you have to, if the user wants that what is the value of P attribute for this field, then you need to fetch that data in SQL
But
query, right?
sir, we do have the information of P in T1, isn't it?
Yeah, so that you have, but the problem is then you are not able to join it. Getting the point?
Okay. Okay. So
Yeah.
to join T1 and T3, we need T4. Is
Yeah.
it like that?
Yeah, exactly. Because if you try to join T1 and T3, how will you join? RNS PQT. There is no common field, right?
Okay. Okay, sir. Yeah.
Got the point? Okay.
Yes, sir.
Fine. So yeah, by the way, that is a good doubt, because yeah, so thanks for asking that, because yeah, I should have discussed it. This thing is very important, as because if you remove this T4, since we do not have any functional dependency or anything over here, then the problem is later on when you have to do select star from T1, or let's say select whatever, select some XYZ value, where you are writing SQL query. So you are writing select some fields. I am not worried about the fields. Then you are writing where. After writing where condition, you are writing T1 joins T3, or let's say T3 joins, yeah, T1 joins T3. For as of now, just think T4 is removed, because there is no information of functional dependency or anything in T4. So you have removed T4. So now you want to join T1 and T3. How will you join it? Because you know, while writing SQL join statement, we need to provide a field, right? We say that student comma employee, student comma courses, where student dot course ID equal to course dot course ID. So we give that kind of thing. Right? Student dot course ID equal to course dot course ID. That means that course ID field is common. So here, if I want to do join between T1 and T3, then I will have to write T1 select star from T1 comma T3, where T1 dot some field equal to T3 dot some field, and that some field should be the common field between T1 and T3, but we do not have any common field between T1 and T3 here, right? And that's why we need the P value in T4. So now if I want to join T1 and T3, I will write select star from whatever, select star from T1 comma T2 comma T3, where T1 dot P equal to T4 dot P and T4 dot R equal to T3 dot R. That is your SQL query. When you write the SQL query, this is what's happening internally. The database is not represented internally in the T table. I mean, so you as a person might see the T is the whole table, but internally the database is represented as T1, T3, T4. And this is how the normalized database is working when you are writing that join statement or form statement in SQL.
Sir, in short, we are creating the constraint for T4. That is, R can determine P and P can determine R. Is it?
Correct. Correct. Correct.
Okay.
Yeah. Yeah.
Okay.
You obviously can say that because otherwise you cannot join. Yeah.
Yeah. Okay.
So, but one thing is you do not have to worry about that explicitly because that will anyway get created unless and until you say that this is getting created, but there is no information about it. So let's put it in dustbin. If you don't do that, then anyway, it is normally getting created. You separate out RNS, whatever is the subsidy, it is left over, that is RNP. So it is there.
Sir, but
So
the problem.
actually, I was throwing it in a dustbin itself.
Yeah, I understood that. That's why I said.
Sir, but the problem is when we try to say R determines P and P determines R, it makes each of them
So
alone as
where am I saying R determines P, P determines R?
I think somebody asked this doubt.
No. We are not determining R with P and P. No such thing is happening. There is no information regarding R and P's interrelation. Okay. Have I written anywhere over here R determines P, P determines
No, sir. Somebody asked, that's why.
Okay. No. We are not doing that.
No, I asking about in T4. In T4 table, the R and P are determining each other.
No, it's no such thing.
No relation.
But sir, we are joining, right?
So joining, when you are joining, as I said, when you are joining T4 with T1 or let's say T4 with T3, any one of them. So the thing is, you are joining the two R's together. You are not joining R with P. You are joining T3's R with T4's R. But by joining T3's R and T4R, you will get a table, let's say T34, and that table will have attribute R, S, and P. Now this P you got while joining these two R's, you got the P over here because of T4's P attribute. There is no dependency or relation or whatsoever, any kind of data relation between R and P. R and P just randomly. R must have some value, P must have some value, that there is no relation or no pattern between either of them mutually, right? Random values. But when you are joining these two T3, T4R, then you get this P in this new intermediate table T3, 4R. And then again, when you join it with T1, then this R will be, then this P will be helpful for you because now this P will help you to join. Okay, so that is the point.
Okay. Now got it.
Yeah. I should not delete it anyways. Let it be here. Yeah. Okay, now let's go to the new normal form, which is now 2NF we have reached. That somehow we managed to reach 2NF. The next is third normal form. Fine. Okay, now what is third normal form? So if you see 1NF, and again if you can make up some values as I discussed with one example, but that also was not a proper example. But if you take some time and make some values, you will see that the redundancy is getting reduced once you go from 1NF to 2NF. And I think in the slide also sir has given some example. That data set you can follow. That will be a proper data set. So from that you can understand that the redundancy or repetition of similar entry is getting reduced. Now when from 2NF again we can go to 3NF. Okay. I will not create a data example for 3NF. Again, you can watch that in the slide. Sir has given the data example. But let us now discuss the rules. So what is 3NF saying? 3NF is saying the checking condition is, let me write like this. And this is a little bit, 2NF and 3NF are a little bit difficult. BCNF is very simple. That will take 5 minutes. So checking condition is, I state like this. Table is in 3NF if for all the functional dependencies applicable on T is the table, right? On T, either of these two are satisfied. And for all the functional dependency, let's say the functional dependency is x goes to y. Okay, so let's say you have a table T and you have the functional dependency. I mean, generically, I am saying that all the functional dependency represented as x goes to y. Some x may be a set of attribute, y can be a set of attribute. So for all the functional dependency, if the two condition, either one of them must satisfy. I will mention two condition now, either one of them. Anyone, if it is getting satisfied, then it is fine. So the first condition is x is a super key. Condition 2 is okay. So either x, both can also satisfy. So what I mean is either or. So this is in either or. So either x is a super key or y is a prime attribute. If both are satisfied, very good. But if any one of them is also satisfied for all the dependencies, okay, please, this is very important. For all the functional dependency, you have to apply these two rules and check whether that functional dependency is falling in one of the category or not. If it falls in one of the category, it is fine. If it does not fall, then you are in, I mean, again, it is not in 3NF, right? So, okay, this is a formal definition of third normal form. But for solving our questions, we will follow another way of solving it. Basically, this definition also derives to that trick or that way of solving the question only. But for your ease of solving question on the run, so we will follow some other technique. Okay, I mean that is a kind of trick you can say or something, or technique. But this definition only points to that way of working. Once you figure both these things out, you will be able to relate both of them. But we will see that technique or that thing. How do we do? So if this is the technique, I kind of feel a little bit reluctant about writing technique and these things, but basically this is the definitions corollary you can say. But anyways, let us keep it like this only. If there are two functional dependencies like x goes no, let's not use x, let us keep something else. Let's say like a goes to b and b goes to c. Okay, and where a, b, c, all of these can be a set of attribute. Don't assume these are atomic attribute. I'm using a placeholder, right? Where a comma b comma c are all element of, let's say, the set of attributes. So how can I refer to that? Let's say attribute set, maybe I can define it as D. Okay, D ATT. Okay, what I mean by this is that they are all a set of attributes. So if I have these two functional dependencies where A determines B and B determines C, and B is non-prime, yeah, B is non-prime attribute. Okay, then we will say that this is no longer a third normal form. So A determines B, B determines C. Now B is a non-prime attribute. Okay, so if you apply the first rule in this case, so let's say X is a, in this case X is A, right, in this example. So because X is the left hand side, so if I say A goes to B and X is a super key, so X is a super key means, okay, that is, there is no problem with it. But then I am saying if X is a super key, then this is satisfying, and then it is saying B goes to C is there, and I'm saying B is a non-prime attribute. Okay, I have not told anything about C. Okay, let us say that C is also non-prime attribute. Okay, now if this is the situation, can you say that it is going according to the first two conditions that we discussed? I mean the definition, these two things.
Yeah, the second rule applies, sir.
So let's say Y is a prime attribute, we are saying, right? In the second rule, it is saying X is a super key or Y is a prime attribute. Any one of them must satisfy. So if I say that A goes to B, X is not a super key. I mean A is not a super key, sorry. Assume A is not a super key. Okay. And I have already said B is non-prime. Okay. So if A is not a super key and B is not a prime attribute, then neither of these two conditions are getting satisfied.
Yes.
And at the same time, B goes to C is there. So then, since neither of these are getting satisfied, then I can say that this is, I mean, it is not in 3NF. It is, since we said that for all functional dependency, either of these two must satisfy. Okay. Now in this example, since A goes to B is there, and I am saying A is not a super key, so I have given that A is not a super key. I have explicitly mentioned that. Assume. So if A is not a super key and B is not a prime attribute, then obviously neither of these two conditions are getting satisfied. Therefore, A goes to B and B goes to C creates a transitive dependency. You know, transitive in mathematics, you must have done set theory and all, transitive behavior, in which we have this common B, or let's say in set theory, you know, the transitive pair, right? A comma B, or let's say A related to B. But you guys have learned relations, right? Or no?
Yes, sir.
So A related to B and B related to C, then I can say A related to C. If then if this is so, if this is implied, then I say that R is transitive. So this is something like that. So if I have A determining B, B determining C, and these two conditions are not satisfied, either of these two, then I can say that this is transitive dependency. So the difference between the definition part and the technique part is, what I mean is, you will have to only see for transitive dependency when you see such a pair of dependency where you have the right hand side of one dependency as the left hand side of another dependency. If that is not the case, then you don't have to search for 3NF, I mean these transitive dependencies. Okay, by the way, these are called transitive dependencies. Previous one was partial, this is transitive dependency. So a transitive dependency will always exist in pair. Okay, A goes to B, B goes to C, or whatever, P goes to Q, Q goes to R. But only thing is, we will apply the two rules that we learned on top. X is a super key, Y is a prime attribute. If these two things we will apply, any one of them gets applied on that, I mean on the functional dependency, then it is not, then it is basically not a problem, then it is not a transitive dependency, right? So by the way, let me just rephrase it and state like this. If on a particular functional dependency, let's say f dash, the rules are not the rules, the conditions. neither of the conditions are applicable, then we call this that dependency f dash to be transitive dependency. Fine. So that is the definition of transitive dependency. And if there are transitive dependency, if there are transitive dependency in a table, it's not in 3NF. Okay. So again, we will find out pairs of dependency where A goes to B or B goes to C form is there. That is the right hand side of one dependency is there on left hand side of another dependency. And then we will apply the two rules. If either of them gets applied, it is fine. If none of them is getting applicable, then I will say that, okay, this is a transitive dependency. Now let us start. Let us take one example and see whether we can figure out. So,
do you mind scrolling up a bit again, just for a second? Just for a second. Yeah, I'll take a screenshot.
We will give these things. Okay, don't worry.
Yeah, I just want to, like, before we move ahead, I don't want to be like in a confusion, so I just wanted to make sure I understood. Just give me a second. Okay. You're done, man. Thank you so much.
Yeah, no issues. So again, just what is the technique part is simple. What we will do is you will figure out every pair such A, B, B, C pair. If there is no such pair of dependency, then forget. Don't worry. That's why I gave you this relations example, which you guys must have learned in maths courses, right? I mean, I just gave one example. You guys have learned relations, right, or not learned? I don't know. Anyone can corroborate with that?
Yes, sir. In maths 1, it was there.
Chalo. So then maybe you guys are familiar. So we have this transitive, symmetric, reflexive relations. All those things must have been there. Anyways, so what we will do is we will figure out such pairs of dependency where the right hand side and left hand side are repeating. In one of the dependencies, right hand side is there on another dependencies left hand side. A, B, B, C, this kind of feature, and then we will apply on both those dependency. We'll apply the two rules. These two rules. Okay, and then we will understand what is happening. So now let us take one example and let us see whether it is third normal form or not. Table is A, B, C. Let me take another color. I'm bored with green. Table is A, E, C, D, E. Okay, functional dependency set is again, I think this is very common example in many books. Okay, right. By the way, I forgot about one important point to mention over here. So the person who just took a photo, you maybe just need to add one thing, that is third normal form. A table is in 3NF. If for these are the things, if it let's add one more point here. Firstly, which is already in 2NF. So in order to get to 3NF, you have to at first reach 2NF. Now once you get to 2NF, then you apply this rule. Okay, you cannot just from a table you cannot apply 3NF rules like this and say that it is in third normal form. No, at first you have to reach second normal form, And then in order to improve further, right, in order to improve further, then you have to apply this transitive dependency checking. And if you find a transitive dependency, then you say that, okay, I have already eliminated partial dependency and that's how I reached 2NF. Now I have removed, now I am checking for transitive dependency, and if I find a transitive dependency, then I will say that since there is a transitive dependency in my table, therefore it is not in 3NF, but it is already in 2NF, that I know because I removed all the partial dependencies. And now I will try to remove the transitive dependency that I found, and then I will reach 3NF. Okay, so that is the course that we will, that is the pathway. Okay, now, so first of all, 1NF, obviously T is in 1NF by default. We already discussed that part. Now let us check for 2NF. First is we have to convert it into 2NF. So candidate keys.
AB.
AB candidate key. Anything else? D, E, C. So AB, okay. A, B, C, A, B, B, D, A, B. So A, B is the only candidate key. Fine. Prime attributes A and B. Okay.
B gives D is giving the trouble.
Yeah. So partial dependency is there. Partial dependency. B goes to D. Correct. Okay.
So we
There.
split in two tables.
Yeah. So T1, BDE.
Yes, and T2 ABC.
Correct. Okay, ABC and BDE. Okay, fine, everything. Apply the FDs. So if
D
I apply
gives
the,
DE.
very good.
And D gives E.
Very nice.
And AB gives C in the second table.
Yeah. So already in 2NF, no problem with any dependency or anything. Right?
Yes, sir, both are in.
Yeah. Okay, so 2NF reached. So till this point, okay, now we will check for 3NF. Okay, so let's take blue color. Checking for 3NF. So okay, first let us do it on T1. Okay. So as I said, we will find what did we say? Step 1 is find pairs of dependency of form A, B, B, C. Do we have any such thing in T1?
B gives D and D gives E.
Correct. So B goes to E.
Yes, sir.
And
D.
sorry, B goes to D. B goes to D and D goes to E. Now, what was step 2? Apply the checking rules. What were the rules? For both of the, I mean, for each functional dependency, check either the left hand side should be a super key or the right hand side should be a prime attribute. If that is satisfied, then I will say this is not a transitive dependency. So let us check this one. B goes to C, D. Is B a super key?
Yes, sir.
Correct. So B goes to D. Left side is super key. So not transitive dependency. The other one?
Sir, it is not in.
So is the left side super key? No. D is not a super key. Is the right side prime attribute? No. Neither of them. So neither, I'm writing this much because this is the first example. After this we will not write. Neither left side is super key nor right side is prime attribute. Therefore, D goes to E is a transitive dependency. Now this is problematic. So we know that T1 is not in third normal form. So we have to do something and remove this transitive dependency. The process is exactly same. Now this is the beauty. And the process of removing dependency is same. Whatever primary, partial dependency, transitive dependency, all are same. The checking rules are just different. Okay. So what is the process? So let's remove
D plus.
Remove D goes to E. Yeah. So we'll step 1 is D plus.
DE.
What is D plus in this table?
DE.
DE.
So we will look into the T1 table.
Correct. T2 table we have not yet reached. Let us
Oh.
figure out T1 first, then we will go for T2. Right? So that's why I said checking for 3NF on T1. Under this we are doing all of this. So remove D determines E in, and then we were finding DE. So then step 2 is decomposition of the table. What is this? T3 I think, right? T3. T3 DE.
Oh yes, DE and BD. T4 will be BD.
Very nice. Chalo. So we have these two tables. Same step repeat again. FD, what is the
D
functional
determines E.
Correct. What is here?
B determines D.
So there is no trouble because only one dependency. Obviously it is in second normal form. Obviously it is also in third normal form. So therefore 3NF, 3NF. Because you check for partial dependency, obviously not there. Transitive dependency also not there because there is no pair. Only one dependency is there, so don't have to worry about anything. So okay, so these two are done. Now we have forgot about this T2. So now we will work on T2. Okay, if let's do it on the side, I think, or yeah, below only. So checking for 3NF on T2, right? Now, so what will happen in this case? Now I will not write. So first we have to figure out if there are pairs of dependencies, right? Like this, same step. Find pairs of dependency. So do we have any pair of dependency where AB goes to BC, that kind of stuff?
No, sir.
No, right? Again, let us see the primary dependency set. Can we figure out any such dependency that I can make in T2? No. B, D, E, no. Neither way. It's not possible. So since I do not get any such dependency where I have this pair A, B, B, C, that kind of stuff, therefore no need to figure out anything. We can say that it is trivially in third normal form. So since no such pair of dependency present, therefore no transitive dependency, therefore T2 is in third normal form. Fine. So that's your solution. So if I ask you that what is the final T2 already in 3NF. So what is the solution? So the final 3NF decomposition.
T2, T3 and T4.
Correct. T2, which is basically your ABC, right? T3, which is basically your DE. T4, which is your BT. Okay, so all of them are in your 3NF. Each of these table are in third normal form. Okay, one important property you can waste some time, not waste, you can give some time and figure this out, check this out properly. But you can also just remember that third normal form always, or let's say it in this way, that decomposition or normalization, whatever you want to say, normalization till 3NF preserves what BCNF okay. So keep this property in mind. Whatever dependency you had initially, right, over here in the primary dependency set, yeah, so this primary dependency set, whatever dependency you had initially, till decomposing till third normal form will keep all those dependencies available. I hope you guys, if you are not very familiar with week 5, then I think you will be in trouble. But when you learn week 5, you will see that there are two main aspects. That is, one is lossless decomposition, another one is dependency preservation. So dependency preservation aspect of decomposing a table is always let's say satisfied, or basically all the dependencies of the primary dependency set, this set, right, this set will be preserved till you do normalization up to third normal form. After third normal form, if you try to go to Boyce code normal form, BCNF, then it is not that always it will happen, but sometimes the dependencies, primary set of dependencies might not be preserved. All the dependencies might not be preserved. Some dependencies might be lost. So what do you mean by lost? So what I mean is, so let's say your decomposition of the tables are such that B determines D is not applicable on any table itself. So suppose just for the time being, suppose I have only two tables, ABC, one decomposition, and the table is DE, or let's say B goes to D, right? So let's say ABCE, I need to have a common attribute. So let's say ABCE and DE. These are the two tables I get into a decomposition. And just for the time being, suppose these two are the BCNF decomposition of the given table. It is not, but suppose it is so. Then you see that in this table, D goes to E dependency is applicable on this table. This is T2, this is T1. ABC is applicable on this table. So these two are satisfied, but B determines D is not applicable on any table. So this might happen when you go till the decomposition of Boyce code normal form, but till third normal form, it will not happen. So keep this thing in mind. It might come as a MCQ question.
Excuse me, sir.
Huh. Tell.
Sir, in this S2, I'm not actually getting why we are not removing B goes to D, but removing D goes to E. The second, apply the check rules in S2.
Okay,
this
one,
I got,
right?
yeah. S1 I got, yeah. But below that, S2, apply the check rule. Yeah.
Acha. Okay, so why we are not removing B goes to D and why we are removing D goes to E, right?
Yes, sir. Yeah.
Okay. So as I said, let us go to the condition. So if you see over here, what is the technique that we talked about? That if there are two functional dependencies like A, B and BC, that is one's right hand side and left hand side should be common between these two pairs. Just a second. Okay, so if there is a common like this, then we will figure out that if X is a super key or Y is a prime attribute. Now, if you look at it from this point, B goes to D, see the left hand side is a super key. Why? In T1, what is the super key? B is the super key, right? B is determining D, E, all of them. So B is a candidate key. B is also a candidate key is itself a super key also. So B is a super key. Getting the point? So since left side is a super key, therefore according to this condition, right over here, the first condition, it is I'm quite
That
sorry.
X is a super key.
Yeah,
That
yeah,
one,
X is a
no?
super key. Yeah. So you see, left hand side is a super key. I'm quite sorry. I have to take this call. Okay, just give me 2 minutes. Huh? Sorry for the delay. Hello. Sorry for the delay. Kind of emergency situation. Anyways, so yeah. What were you asking? I think.
Why we are not selecting? Why we are removing D?
So yeah. So as I said that after you take, after you find out these two pairs, right, where you have the left hand side and right hand side and left hand side common between the two dependencies. So let us check these pairs in this example. In T1, I have BD and DE. So I have this D as the common part, right? In that example, we have A goes to B, B goes to C. So this B, that common part is over here within these two pair. Okay. Now we figured out the pair of dependencies. Now I will apply the two condition on each of these pair. Each of this pair, I will apply these two condition. Right? Not each of these pair, basically each of these two dependencies in the pair, I will apply these two condition and figure out whether one of them is getting satisfied on both the dependencies or not. Right? So what are these condition? X is a super key, Y is a prime attribute. Either one of them must be satisfied. So, and what is X and Y? X is the left hand side, is basically X is basically the left hand side, Y is basically the right hand side. So when I'm writing X is a super key, what I mean is left side is a super key and right side is a prime attribute. If either of them, see this or is very important. If either of these two is getting satisfied, then I will say that our dependency is not a transitive dependency. Okay, now Let us go to this example. So you see B, you are saying why we are not removing BD. So you see BD is here, and let us apply that. What is the left side, which is B? What was the condition? Left side can be a super key and right side is prime attribute. So is left side a super key?
Yes.
Right, correct. Left side is a super key. Why? Because in T1 table, B is the super key, and because B is the candidate key, because B is basically determining B, D, E, all of them. Right? Yeah. So here you see B is determining B, D, E, everything. So therefore B is candidate key, and that means essentially B trivially is also a super key. So that means left hand side is a super key. So coming to this condition, left hand side is a super key. This is getting satisfied. So since it is getting satisfied, I am not worried about that particular dependency. But let us now come to D and this D second one. Again, we will apply the same thing. Either left side should be a super key or right side should be a prime attribute. So is left side a super key? Is D a super key? No, right? In T1, D is not a super key. Yeah. So in T1, D is not a super key. So since D is not super key, okay, fine. But still we have another condition left. If that condition is getting satisfied also, then also we will not worry. So what is that condition? Right side must be a prime attribute. Is right side a prime attribute? Is E a prime attribute in T1? No, right? E is not a prime attribute. So since E is also not a prime attribute, therefore that means neither of those two conditions is getting satisfied, but we had this pair BDDE so that we have this common feature. So that is what transitivity looks right? That's why I wrote ARB, BRC, that means ARC. This is what transitive dependency means. What transitivity in the essence of mathematics, transitivity means this. So if I have this kind of pairs where the right and left side are common between two dependencies, like in this case D is there, common on right side in one and left side in another. If such a pair of dependencies are there, then I will apply these two conditions on each of those dependencies and see whether it is transitive or not. If either of the conditions are getting satisfied, then I will say that okay, one of the condition at least is getting satisfied on both the dependencies. That's why none of them are transitive dependency. If none of the condition is getting satisfied, I mean neither of the two condition is getting satisfied in any one of the dependency or on both also, but basically in any one of the dependency, if it is not getting satisfied, then I will say that particular dependency is a transitive dependency because it is not satisfying the criteria, therefore it is a transitive dependency. Now since that is the transitive dependency, we will remove that dependency, not the other one. Is it clear, or any doubt you can ask if you did not understand?
Yeah, I got it, that part. So while creating the table, we are the one who will decide which key will be the prime attribute or a candidate key, right? And after that, we are discovering whether it is a covering any transitive relation or not.
Yeah. I mean, so let's say in that you have this T1 table, right? Just see this part. See this part. So you have this T1 table, BD, forget about all other things. I mean, initially after forget everything, just assume you are given a new question and that new question is T1, BDE 3 attributes and it has the two functional dependency, B determines DE, D determines E. These are the two dependencies given to you on new table T1. This is completely a separate question. Now I ask you what is the candidate key of this table? Okay, so your answer will be obviously B because yeah, B is a unique attribute which can determine all of them. So B is a candidate key. Is there any other candidate key other than B in this table? No, right? There is no other attribute. Correct. So that means there is only one attribute which is candidate key. And there is only one candidate key. Therefore, B is the candidate key and that's why trivially B is also a super key. So yeah, that's it. Okay, and then we are applying the conditions.
Yeah, got it, sir. Yeah.
Okay, so yeah, so we have discussed this property of decomposition till normal, I mean, till B third normal form. There are some other examples I want to solve, but let us at first cover the BCNF part and then maybe we will solve one example with BCNF because BCNF will anyway take all the normal forms while solving. So yeah. Okay, so the next Topic is okay, which is your BCNF. Now, this is very simple. What did 3NF said? 3NF said that all functional dependencies must follow either of these two conditions. This is what your third NF said, okay? But let me write, then you will understand why I am writing the same thing in BCNF also. Left side is super key, right side is prime attribute. This is what 3NF said. BCNF is saying, just remove this. So, and either part, all functional must follow. So this is what BCNF's definition is. 3NF was allowing you to satisfy two condition. BCNF is saying, okay, I will restrict furthermore. I will only allow you to satisfy, I will only allow you to be called in BCNF, Boyce code normal form, when that all the functional dependencies of the table satisfy this condition. Left side is super key. Now, that means what? If I give you a table T, and if I say, let's say A, B, dot, 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 let's say up to E, and then I say that you have a functional dependency set, let's say A, B determines C, let's say D determines E, let's say that I say B, D determines A, okay. Let's say these are the functional dependencies I give you, then I can only tell that T is in Boyce code normal form or BCNF when each of these functional dependency left side is a super key in case of each of these functional dependency. Now, how will that be possible? Basically, the thing is, when you basically decompose all the, decompose the table in such a manner so that all the applicable functional dependency on that table serve as the super key. The left side of that functional dependency serve as the super key. Okay, so that is the thing. So if I separate out the table ABC, okay, then I separate out DE. In this example, let's say this is what I do. T1, T2. So what are the applicable functional dependencies? T1, AB determines C, here DE. And what happened with BD goes to A? Can I apply BD goes to A somewhere?
No, sir.
No, right? So I cannot apply BD goes to A, not applicable on any table. After decomposition. So therefore, refer previous condition. Okay. So dependencies might get lost when you go up to BCNF normal form. So now if you see these two tables, T1 and T2, you see that AB determines C and here D determines C. So you have these two functional dependencies applicable, and both of these functional dependencies, the left hand side is super key in their own table. So left side is super key. Okay. So this is Boyce code normal form, nothing different over here. Just that you have to decompose so that all the applicable functional dependencies have their own attribute set and they form a new table. Okay, so now let's take one example and solve it, and then maybe we will close for today. One topic will be left, that is your fourth normal form. I think that we might cover in the next session. That is quite easy also, not difficult.
So when we already have 3NF
Ah,
and we are not losing any dependency in 3NF, why are we going for BCNF?
Because the main thing is we were not targeting for dependency, we are targeting for redundancy. We want to reduce redundancy. So once you see the table, right? So that's why I said that if you see the table populated with data, a table populated with data which is in third normal form, and another table populated with data which is in BCNF, you will see that even third normal form might have some redundancy. BCNF will also not have that much. Why? If you ask why it is so, the thing is, if you see the third normal forms condition, these things you have to think on your own a little bit, and you will observe the pattern. So only difference is that BCNF is saying X must be a super key. For every dependency of the form X goes to Y, X must be a super key, that is left side must be a super key. Third normal form was allowing this much relaxation. It was saying that at least, okay, even if left side is not a super key, even if you have a prime attribute on the right side, then also I will allow. I will say you are in third normal form. BCNF is saying no, I will even not allow, even if you are have a prime attribute on the right side. The thing is, it's not always that non-prime attribute causes redundancy, right? Prime attribute can also cause redundancy. In fact, the example that we took, I mean, this happened coincidentally, but somehow in this data example that we took, C was a prime attribute, right? For our, I mean, for the sake of discussion, we did not take C as prime attribute because it was taking some more time to create some example. But AC was one candidate key, AB was another candidate key. So C was kind of C is actually a prime attribute. But then again, although C is a prime attribute, still you have this feature of B2, C2, again B2, C2, again if I have B2, yeah, again B2, C2. So it's not that only non-prime attribute causes redundancy, prime attribute also causes redundancy. Only thing is, since prime attribute are part of a candidate key, it is less probable that they will cause redundancy because they are kind of, I mean, since they are part of candidate key, they are also defining some other fields. That's why they are part of candidate key, right? So therefore, since they're defining some other fields, it is said that there is a lesser chance that they are also getting repeated and some other value is also getting repeated. I mean, that way. So yeah, so you have to think, you will understand that what I'm trying to say. But in this example, I think it is very highlighted that C is a prime attribute, but still it is having redundancy. So BCNF will also not have this. BCNF will not allow this, but 3NF will allow this.
Got it, sir.
Yeah. So the only difference between BCNF and 3NF is this second condition is not allowed in BCNF. BCNF is restricting you that every functional dependency must be a super key. I mean, the left side of every functional dependency must be a super key. Okay, now this example, let's take one example. A, B, C. T table has A, B, C, D, and the dependency set is AB goes to C. Okay, so now let us start from 2NF. So first is candidate key. So if I see DC is there, that means AB. Okay, so AB, if I have, yeah, so AB is the candidate key, right? Do I need any other candidate key?
No, sir, there's no.
Correct. So therefore, we will check for partial dependency. Is there any partial dependency?
No, sir.
No, right? Because we do not have B goes to something or something like A goes to something. So it is fine. So no partial dependency. So first is no partial dependency. Therefore, 2NF. Already T is in 2NF. Second point. Okay, so second is what? 3NF checking. Transitive dependency. Okay, we have this thing B goes to C, C goes to D. Sorry, B goes to, yeah, B goes to C and C goes to D. So basically we have this Oh, wait, just a second. Sorry, this is AB goes to C, right? Then again, this is I have B, but then this B will not be considered because then both of them are composite attribute and I cannot break left hand side. Right hand side we can break, but left hand side we cannot break. So we have no transitive dependency as such, but even if I apply the rules that left hand side must be a super key and right hand side must be a prime attribute, either of them must be satisfied in both the cases. AB goes to C, obviously left hand side is the candidate key, so it is satisfied. And BC goes to D. If I apply that BC goes to D on this dependency, if I apply the rule that left hand side must be a super key or right side must be a prime attribute, is it satisfying or is it violating?
No, BC is not a super key, sir, so it is violating.
And D is also not a prime attribute, right?
Yes.
Because our candidate key is AB. So let me write it over here. BC not a super key and D is not a prime attribute. Therefore, BC determines D is transitive dependency. Okay, so since we have found one transitive dependency, we have to separate it out. So separate out. What we will do BC plus B C D. So step 4 T2 will be BCD. T3 will be BC comma AD A, sorry, right? Yeah. So we have these two tables. Now let us apply the FDs ABC, okay, and BCD here. Any other FD applicable? No.
No, sir.
Right. So therefore, if I again apply the transitive, to check for transitive dependency, I will not find anything. So therefore, 3NF. Sorry, third normal form. Reached. Okay. Then fifth is checking for BCNF. Okay. Now, if I see that all the applicable functional dependency, left side should be a super key. So all the applicable means only one dependency is here and only one dependency is here, and in both the cases, left side is basically super key already. So therefore, yeah, so it is not only in 3NF, but also it is BCNF. Fine. So now that is the whole from 1NF to, so this is the final result, I mean. So your complete normalization 1NF, 2NF, 3NF, 4NF, and not 4NF, BCNF. 4NF is multi-valued dependency, not multi-valued attribute. First NF was multi-valued attribute. Fourth NF is multi-valued dependency. Two are different things. That was attribute, and fourth NF is multi-valued dependency. This comes after BCNF. That I will not discuss today. We will do that next day, and that is very easy also. I mean, not something, and that is not that important also. Just one last point I would like to, one last question thing I want to give. Tell me what will happen in this case. I know you might be worried that, okay, this is kind of very big and it will take time. Let us see. Okay, just for the, even if it takes time, solve it. I will not solve it completely. So these are the, this is the functional dependency. ABCDE, suppose that is the table, and I want to find out, I mean, convert it into Boyce code normal form. I mean, break it down into decomposed tables so that each table is in BCNF. So if I try to find the candidate key, then I will see what is on the right hand side, not there on the right hand side. So A, D, E, B, C, A, B, C, D, E, all of them are on the right hand side. So I
Yes.
don't get, right?
A is
So,
the candidate key and E is also the candidate.
so okay, so we have to figure out slowly. A, let's start from A. Is A candidate key? A, B, C, 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 B goes to D, right? So A goes to B, C, B goes to D. So that means A, B, C, D we have.
And E will be left out, so E also.
CD will give the E.
CD will give E. So therefore, A
E is
is one candidate key.
is
Okay.
E is also because E determines A. So
Correct. So E determines A, therefore automatically E is a candidate key.
and CD
But
is also.
CD determines E, so CD is a candidate key. Anything else?
No.
So BC will give CD. So BC will also become.
BC will give CD, BC, B will give D, correct. Yeah. So BC. Right. Anything else? A, B, A, B, A, B, A, B.
So we cannot combine A and E
Sorry,
because
sorry, A is already there. So BC is okay. So all okay. Anyways, all the attributes are covered up because we can see there is no other attribute left, so we cannot combine anyways. C we cannot combine. B anyway it's there. B alone cannot do anything. Yeah, I think that is it. So these are all the candidate keys that we got. Yeah. Okay. So that means the prime attributes are?
So everything becomes prime.
All of them, right? A, B, C, D, E. That means? What does that mean?
That 3F will always be satisfied. Whatever is on the left will be prime.
Correct. So whatever is on the left side,
RHS.
right side, yeah, right side will be condition was left side super key, right side should be prime. So whatever is there on the right side will be prime attributes. So I do not need to check anything. I can directly say that this is already in 3NF. Only thing is now I have to check. So sometimes they will ask you that what is the BCNF form of this table. And if you make a mistake in finding the candidate key in the first step, right, then you will not get all the prime attribute over here. And then you will go on solving partial dependency, transitive dependency. But if you do not make any mistake in finding candidate key, then all the prime attributes are covered up and you don't have to solve that much. I mean, then only thing is now you have to apply check for BCNF. BCNF is saying every attribute should be a super key. So that is very easy. Just separate out each attribute into a table. Make this one table, make this one table, like that. So make ABC one table. CC is common between them. So let's say CDE is one table. Right? Again,
So
BP
B gives D will give trouble, so because we do not have.
Which one will give trouble? Sorry.
B gives D.
Why?
So because LH is okay in separate table, it will be a super key. B will be a super.
I'm checking for BCNF.
Okay.
Because 3NF to ho gaya na, also already in 3NF. So I have to check whether it is BCNF or not. Obviously, it is not BCNF because BCNF each table, each functional dependency must basically have the left hand side as super key. So that can only be done if I create all of them separate table, put all of them into separate table. So obviously, each of them will be the left hand side will be super because I'm only putting that many attributes. So this functional dependency I make one table. This one I make one table. This one I make one table. This one I make one table. Only thing is I have to be aware that all these tables have common attributes. Otherwise, it will not be a lossless decomposition. So if I let's say make this T1, I also did not check that, but let us see the T2, T3, T4. Right. So if I check between T1 and T2, obviously left hand side will be prime attribute, a super key in all of these cases. So BCNF to ho gaya. So all of them are in BCNF. So BCNF, BCNF, dot dot dot. All of the it is also BCNF. It is also BCNF.
So
that is fine. Just a second. Let me just complete this checking. So now all of them are in BCNF, but let us check whether it is lossless or not. So that means there should be a common attribute, and there should be, I mean, that common attribute should be able to serve as a super key. Sorry, serve as a candidate key in one of the table. So let us take T1, T2. Common attribute is BC. C is the common attribute. right? So in this
Yes.
case, C cannot serve as a
Lossy.
lossy decomposition. So let us forget about T2. Can I join between T1 and T3?
No, sir. Again, no,
Why?
sir. So B is the common. Yeah, B is super key in T3. Sorry.
See it over here. T1. Let us see over here. T3, T4. Over here you see T1, T3. If I join,
Yes, sir. It is possible. Lossless.
yeah, T1 and T3. So what is T1 and T3 if I join together? So if I T1 3, let me just write it like this. T T1 3. What will be T1 3? ABC and
And
D.
D and lossless, obviously. Okay, so that is done. Now T2 and T4 are the ones which I have to join. Can
So
I?
T2 and T4 can be joined, sir.
T2 and T4 can be joined. Why? Because E is common.
E is common.
Yes.
Okay. So again lossless. C, D, E and A. This was also lossless. Okay. Then can I join these two together somehow? Common
T1
is
and
what?
T4 also.
Yeah. AA is common. C is common. D is common. Right. So ACD is common. Correct. So can ACD serve as a key in any one of the table? Obviously, in both the table. I mean, even if I say CDE, it is also serving, right? I mean, CD itself is serving as a common in A. I mean, this CD determines E is there. Oh, but A is not. Yeah, exactly. Yeah, CD. If I have this CD, CD is determining E. So if I say that, let's say CD is determining E, fine, okay. Now you know that if I add A on here, I can also add A over here, right?
Yes, sir.
So that means what? If I have ACD, that means it is determining EA and CD, right? So EACD, which is basically this table, common. So again, I can join these two, which is T1, 3, 2, 4. This is also your lossless decomposition. So basically, you can figure it out like this. You can join it in this manner, and this will work.
T1, 1 and 4 also.
Done, right? 1, 2, 3, 4 means what? The whole table is, basically this is the original table. This T table, I mean.
Yeah, so just the join sequence we need to see, right? That what to join first.
Correct. So what to join first, that you have to figure out. I mean, that anyway, while writing SQL query, you guys do that, right? If I have course, student, enrollment, I mean, instructor, all these 4 or 5 tables are given. You see that while writing SQL query, which are the tables that you can join first, and then from that, if you are writing a correlated subquery, or let's say subquery, normal subquery also, then in the inner subquery, you write join 2 table, and then on the result that you get from that inner subquery, on the basis of that, you join 2 table on the outer subquery. These kind of things you guys must have practiced in the SQL week. So that is what we are doing. So the sequence of joining might be different, and that is okay. That is not a problem, right? Fine. So yeah, that is it.
Well,
So we learned all the normal forms. Only multi-valued attribute, multi-valued dependency, that is left. That is the 4th normal form that we will discuss in the next session.
sir, I had a doubt in step 1, sir.
Tell.
Sir, normally what we do is we check the entire relation and the FDs, and we check for which is the FD that is causing the trouble, and then we separate it out in a separate table.
Correct.
And then we divide it into 2 tables, and then we again perform the same thing. But
Correct.
here we directly did it, decompose that entire relation into 4 tables because of the fact that every FD was a BCNF.
Every the table was already in 3rd normal form. That's why I will not check all those partial dependency, transitive dependency. So since it is already in 3rd normal form, the only thing left is checking for BCNF.
Okay,
right.
sir.
Now since that is the only thing left that I need to check for BCNF, what is BCNF asking you? BCNF is saying every left hand side of every the left hand side of every functional dependency must be a super key.
Correct.
Now, what does that essentially mean? All the functional dependency that are there, left hand side is super key for all of them. It will only be possible when you separate out them into tables, right? Basically, otherwise, if you have multiple attributes in one table, then how can it happen that all the left hand side can serve super key at the same time? Okay, so
Sir, my question is, the thing is, but 3NF tells us that, if the left hand side is not a super key, then we just check for the right hand side whether it's a prime attribute or not. But,
correct.
in this case, it happens so that the left hand is a super key. But if this would have not been the case, then still we would have taken the entire thing into BCNF,
No,
into
in
separate
this
tables.
case, left side is not super key. In this case, what was the table? This table T, if you talk about, then the table T was, let's say, A, B, C, D, E, up to E, right? Up to E, this table was there. And what was the functional dependency set? This was the functional dependency set.
Yes, sir.
So if all these functional dependencies are applied on the same table, then it is not that the left side is a super key, right?
Yes, not all FDs are, satisfying that.
Correct. So that means what? Then that means it is, although T is there in 3NF, but T is not there in BCNF. Because
Yes,
all
yes.
correct. So that's why we are separating out, so that each of them can now serve as BCNF. Because if you see now, after separating, A goes to BC only applied to this, no other dependency can be applicable to this table. Then CD, E, then B goes to D, and then E goes to A.
Sir, if we go stepwise, then will we end up having the
Same thing.
Okay, sir.
You can apply that also, no problem. Okay.
Yes, sir, got it.
Sir, in this case, if we want to join T3 and T4, we can't do this, no?
No, cannot do that.
So, sir, if we have to do it, we have to again join it with the rest and then take it from there.
Exactly. I think you guys have already done this kind of example in SQL, right? That's what I said, that let's say you have this student, course, and instructor, 3 tables. Now, the student table has SID. What I mean is, this is very common question in many SQL queries. Student table obviously will have SID dot different things, and then it will have the associated course. The whatever course that student is doing. Now, course table will have the course ID as the primary key and some dot whatever field, and then that particular course is being taught by which instructor. So maybe instructor ID. Okay, and then the instructor table will have the instructor ID as the primary key, followed by some fields like this. Now you want to relate that which student has worked under which instructor. That's the thing that I'm asking you. Tell me the name of the student who has worked under instructor Albert Einstein. Okay, so who has worked under instructor Albert Einstein? If I ask you this question, then how can you do it? Can you relate directly between student and instructor? No, right?
No, sir.
No, sir.
Yeah, correct. So this is the same thing. Although you only want to relate between these 2 tables, but while writing query, you will write select whatever star from student, comma instructor, but only by doing this you cannot get the result. So you need course where student dot SID equal to student dot CID equal to course dot CID and course dot instructor ID equal to instructor ID. So this is what you need to do. So here also you cannot directly join between these 2 tables. Right? You need the course table. Essentially the same thing is happening here. Okay, so that's why I told that these are the system subject, right? DBMS is system subject. So if you know this internal, then you can relate it with the query part. So what's happening in the query? Okay, now you can also say that if that is how it is working, yeah, just a second. So you can have this normalized way of representing student table, course table, and instructor table internally in a much more less redundant and more consistent manner, and then the SQL query will work on top like this. So it's not that you need to join T3 and T4. You can join in any order, or as long as it is, I mean, at the end result is creating the main table which was given to you before decomposition. If you can reach that table by any pathway, that is fine. Okay, yeah, go ahead.
Sir, this above table is in BCNF?
Which table? All the tables are in BCNF now. T1, T2, T3, T4.
Yes. Okay.
Okay, chalo, it was quite a long session. Anyways, normalization is very important and quite difficult. Not difficult, as long as you understand it, it is easy. But if you do not understand the steps, the processes, then it is very difficult. If you are not clear about even one step, then you will not be able to solve it. But if you are clear about all the steps, then it is very easy. It's like mechanical work. You just apply the things and you will solve it. So hope watch this session properly. Even if you want to repeat this session on YouTube, please go through it. Yeah, fine.
Thank you, sir.
Chalo, thank you. Good night.
Good night.
Thank you,
Thank you,
sir.
sir.
Thanks.